So I think we can get started. Okay. So I just want to welcome everyone here. And then I think there was a question about is this a conference? So in my email, I mentioned this is like a research retreat. We're trying to imagine big. So the participant, everybody speak with giving a lightning talk, and most people will participate in the breakout room session. So this is what it is. So I will offer some opening remarks here. And the first thing I want to share is that last week, the communication team of our host reached out to try to come up with the message to post online about this exciting event. And they asked me what I feel the most excited about this event. And the thing I shared was I feel excited about assemble such a stellar assemble of statisticians and meeting in person for 2 days to have a discussion, because we can never underestimate the magic of meeting in person and discuss interactively and try to come up with creative and ambitious ideas. So this is one thing I feel most excited about, and I hope you share my excitement of after many years of pandemic where we have this opportunity of meeting together and have this discussion. I first would like to thank our host. We just have a quick look of this very beautiful campus, and it's a young and vibrant university of artificial intelligence. And it's founded in 2019, and it has been making strides in both research and education with exploding visibility. And we have also, just as we have been impressed by how well the city of Abu Dhabi works, this university is also very effectively and smoothly run with a lot of achievements so far. So I just want to quote what the university president, Eric Xing, said on LinkedIn recently. He said, in only 4 years, MBZUAI emerged as a leading institution of AI research, attracting some of the world's brightest minds, securing 18th place globally for AI, computer vision, machine learning, and NLP on CS ranking, carrying out cutting-edge research in large language models, among others, with continuous release of open source models. It's not possible to keep up with all these achievements, and here I just want to name a few that recently MBZUAI published 53 papers in the latest Europes, and also 2 months ago it launched the Institute of Foundation Models, a dedicated research hub for building, understanding, using, and risk managing foundation models, which include the large language models. So which bring me to share the context of this event is as early as the first year after Eric joined the university as its president, and he shared with me that he believes strongly that such a university should have a stat department, which I asked him why, and he said he believes statistics is essential and crucial to artificial intelligence research. So that's why I decided to help the young university envision what the department should look like. And also I suggested this event where we bring in all the active researchers and to talk about research directions and then dream big and try to push forward active research progress. And so with that, I think one thing I would like to accomplish through this event is, I think it can be said, statisticians as a group, sometimes we feel that we're not embracing AI research as much as we should. And then if that's the case, then many of us argue that we should do more. Then the question is how, where, what, who, and how to get started. So we should see this workshop as the beginning of a endeavor we can take together to imagine, to answer some of these questions. And this is the basic idea behind this first AI Quorum at MBZUAI on statistics for the future of AI, and I hope that we will have many of such opportunity in the future. So I just want to thank everyone for investing your valuable time into this venture, and I'm confident that we should be able to build up momentum and find new sources of energy to drive progress in statistics for the future of AI. So with that, I want to invite my workshop co-chair, Hong Tu, to offer his opening remarks. Thank you.
Can you hear me? Okay, thank you. Yeah, it's my great pleasure, to co-organize the workshop with Tian on this. And actually, when she approached me about these events, and I have no ideas. Most of the idea is her ideas. Okay. And first, I want to thank all the participants, basically flying from the US, Australia, and also China, and also UK. And for participants, this is a great event. And I really hope this is provide a platform for all of us, basically, to think about the statistics in the AI era. Okay. And actually, Tian emphasized the 5 deliveries, and actually I wanted to read these 5 deliveries. The first one, we think about a position paper, at least one, okay? And basically we document insight from discussion to guide the statistical approaches in the AI health, okay? The second one is the community, the building initiatives and infrastructures. And actually, we need some specific strategies for fostering collaborative communities with a focus on take advantage of AI approaches. Okay. The third one is education and components. And actually, we need to think about developing new AI-centric courses and revising the existing statistical and biostatistics curriculums to align with the AI eras. The first one is a culture shift in the statistical research. And actually, we wanted to initialize dialogues on shifting the statistical community from many purely theoretical research to the application-driven research while using AI tools. The last one, we think about the cargo style of the challengers. We need to create the practical and engaging events to stimulate real-world application and statistical analysis. And actually, this is the 5 major deliveries we need to think about when we have this discussion in the afternoon programs. And let me start my talk. I try to give a pretty quick talk. Okay. Yeah. Please.
So just before Hong Tu going to the first session, I just want to mention the basic organization is that every morning we will have 2 sessions based on the theme. This morning we will have 1 session on imaging. The second session will be on computational biology, genomics, and each will have a theme with a keynote presentation for 30 minutes and lightning talks. Each will be somewhere between 7 to 10 minutes. And then we scheduled 1 hour, 30 minutes for each of the sessions. So if you do the calculations, 30 plus an hour, we should have enough time for Q&A and discussions. The morning session presentation will be live streamed and recorded. And then I believe that sometime you also would like to post the slides if possible. So you should please work with Phil on that. To make the transition smooth, we preload the slides, so we already have the first session, and then during the break, we'll ensure the second session slides are also loaded. Then we'll have lunch. And we have a short break between the 2 sessions, we'll have lunch. The lunch is another opportunity for us to have a discussion, try to find someone you haven't discussed with in the morning to sit with to have lunch. The afternoon today, we'll have 2 breakout sessions for the 2 sub-areas in the morning, the 2 themes in the morning. And speakers for each of the theme should join the breakout for the theme. Other participants can feel free to join either one. So the breakout will have discussion for 1 hour, 30 minutes, and then each session should have a scriber, some discussion leader, and the discussion leader will have 30 minutes to wrap things up, summarize, while the rest of us have a break. And then we all come back together and then hear reports from the 2 breakout rooms to find whether there are opportunity for synergy. So that's just how the day will look like, and then we'll start.
Okay, thank you. Yeah, it's my great pleasure basically to be the first speaker, and the title of my talk is Revolutionizing the Medical Imaging Data Analysis and Uniting AI and the Statistics for Breakthroughs and Challenges. At the beginning, I would love to thank all my friends for sharing their slides. I copied some slides. I spent the last week for 4 days just to prepare the slides. And actually, there's 3 parts of my talk. And I'll give a brief introduction about the topic. The second one about the AI applications in these areas, and also the opportunities for statisticians in advancing medical imaging data analysis. And actually, I used the ChatGPT to generate these pictures. Okay, I copied the title and asked the ChatGPT generate a picture for me. Okay, that's what the ChatGPT generated. And actually, this is medical image analysis. And use the technique and the process used to create the pictures, images of the human bodies for clinical purposes or the medical science. Okay. And actually, I give a list of the different the medical image modalities and have been widely used for clinical and research purposes. And overall, these imaging methods are essential for delineating the structure and the functionality of organs and the tissues. Okay. And each image modality employs distinct target agents, generating data in various dimensions, extract unique features, and serve the specific purposes within clinical and research context. Okay. You have the big, general picture about this area. Okay. And actually, I started with concrete examples, and this is based on one of my joint paper with Xin Wang on this cardiac imaging. And this is the heart. Essentially, we can consist of 2 parts. One is long vessel anatomical structures and vessel anatomical structures. And actually, you can further divide this structure into different substructures. And actually, you can use different imaging modalities and to investigate their anatomical structures and all the functions. Okay. And also, we further link all these substructures with the different popular the cardiac diseases. Okay. And actually, as the statistician or data analysis, the most important things we are needed to carry out this imaging processing and analysis methods. The purpose is to enhance and extract a signal of interest in imaging data. Well, that's the main purposes. And in general, this field consists of 2 major parts. One is deconvolution, another one is structured learning. And for deconvolutions, you can further divide into the imaging reconstruction and also imaging enhancement. Okay? And for structured learning, and actually we use both of the imaging segmentation method and also imaging registration method. And in terms of the specific method, it's not purely about statistics. You can use the method from engineering, statistics, machine learning, and mathematics. Okay, this field is very diverse. Okay. And actually, I want to emphasize the most important part in the field is about structured learning. And actually, there's 2 major methods. And actually, the most important thing is about image segmentation. Actually, in practice, we pay the bills when we go to hospital to receive the service, okay? And in particular, localize the pathology, all these kind of tumors in the body, okay? And actually, for the imaging registration, it's the most important things. We created Atlas to integrate the data across subjects and the studies, okay? And this is all different major applications in practice, okay? And actually, I used the slides from one of my friends. He developed platforms and basically for processing this kind of light microscopy images. It allowed us to perform the whole brain imaging analysis at the single cell levels. Okay, and this is all the kinds of the tools. The tools called VAA 3D, and actually his group have published many impactful papers, and also these tools have been widely used in the neuroscience field. Okay. And actually, besides the deconvolution and the structured learning, and we use the imaging data and with other data set together. That's basically doing integration, and also in clinical aspect, also do the predictions. Okay. This is the basic general product review about the field, and also I give the second part is about state-of-art AI applications in the field. Okay. And actually, I just mentioned the 4 major AI milestones in the last decade. The first one is the ImageNet. ImageNet is a large-scale database consisting of about 14 million annotated data sets, okay, images, okay? And this database has been widely used in the machine learning and computer vision and for training and testing the machine learning algorithms, okay? The second milestone is the deep learning. And actually, we know that the deep learning really has been widely used and developed in the last decade for both the computer vision and the natural NLP field, and have solved many challenging problems in the field, okay? The third one is by integrating the deep learnings, reinforcement learnings achieved a remarkable performance in several major kinds of problems like the Go and also robotics and other fields, other specific applications. And in the last decades, we see a lot of different products, including published paper in top journals with both Science and Nature. And this is the AlphaGo, and the second one, Alpha and the Fold. And the last one is ChatGPT. I asked ChatGPT to generate his own pictures, and that's what ChatGPT generated for me. Okay, that's the last one is the ChatGPT. Okay. And actually, when you for the whole field of the medical image analysis, one of my friends, Ding Gangshen, has been why you adopt many of these ideas in the medical image analysis. And when I look back almost 10 years later, I see the most exciting kinds of contribution of the deep learning is the development, the architecture called UNet, okay? And there's a series, basically, there's several major kind of review papers on this topic. Actually, the people have used this kind of these tools to do this kind of, to develop the AI tools for do the imaging annotation, okay? This is the one tools developed by my collaborators, Mark. That's his tools. You can use it to annotate the imaging data, okay? This is how I show you how to do it, okay? And also, you can use the deep learning architectures and the tools to solve other challenging kinds of the image analysis problems. This is one of the examples my friend used to do the imaging registration on the surface, for the surface of the data. Okay. And another very important kinds of application is the generative models. Essentially, in statistics, we're think about kinds of data imputation. Okay, this is the examples basically to try to using given the MI to impute the patch, and also given the patch can generate the missing MI data sets. This is the kinds of cross-modality imaging synthesis. Okay. And also, you can use the deep learning and combine with some of statistical models, basically to develop these computer-aided medical data analysis kinds of the pipelines. And then some of the key methods, like this, the neuroimaging, these kinds of nonlinear representation method, like all kinds of these kinds of methods these days. and for this representation learning and the multimodality data fusion and the multi-site data adaptations. And if you ask me what are the two most important challenges, I can tell you, the first one is we don't really understand all the organs and the tissue that much in many cases, complicated cases, okay? And I think that's the most difficult part. The second part is from technology perspective, that's the major heterogeneities within the individual subjects and across the centers and the studies. Okay, that's basically the two major kinds of the challenges from technical side. Okay, and actually, what's the consequences for this? Compared with the ImageNet, and actually for the medical image analysis, the most difficulty is there's no publicly available high-quality imaging data set with detailed annotation information that cover a larger spectrum of the segmentation task in the healthcare, okay? If you could generate the data, this basically the value is more than thousands of billion dollars, okay? Because that's so valuable in practice. And from statistical perspective, and there's some like how to quantify the uncertainties and generalizabilities of the atlases, as well as the deconvolution and the structured learning methods, and also data, the results. And another thing is very interesting, how to develop a reinforcement learning method for various segmentation and regression tasks. And I think the key bottleneck is still the first part, okay, the data size, okay, data set. And the last about opportunity for statisticians, and actually that's the most of the challenging part to me, and to talk about it, because the different people may have the different taste, okay? And Jiankao may have his test, I have my own test, okay? And the different people have the different taste. That's quite common in practice. And I just give you my own opinion about the field, doesn't represent in general. And also Professor Fong has his opinion about the field. Okay, this is very important. The first things, I spent 3 years at the Didi, and actually in the private sector. And actually the most important thing is I changed the way I'm thinking about applications, and also think about the analytical tools, all the methods we developed. And for these days, my personal view is we should emphasize application first, that's the core, and to the ABCs, okay? And the key things is basically we start with some very important applications, dream high, that's the important part. Then you'll move to the data set, okay? Actually, you think about whether you could get a good data set for your problems, okay? And if you could not get to the data set, I just stop there. Don't do anything further. Okay. And besides that, actually, these days, we need to think about analytical tools. Don't have to be a statistical method. Okay? When you're really doing data science these days, you have to learn different kinds of tools from applied math, statistics, machine learning, and engineering. And actually, I really wanted to emphasize these days, engineering is super important, okay? And this is basically tell you how really you deliver the products to the customers, to the students, to the other researchers. It's very important. Other than that, basically the most important, the computing power. This is another very important infrastructure these days. I talked with my friends in Alibaba. He told me these days, what he really care about, number one is the computing powers, okay? He has more than 100 GPUs. And also this guy also from industry also have the 100 GPUs, okay? And also you have human resource. You have the people from the different backgrounds. And in a team, like in a tech company, we only have 10% of people from statistics, a majority from other backgrounds. This is very important days when you really work on this kind of the big problems involved in data science these days. Yeah, I think this is basically covers some of the things I have been doing in the last 20 years. When I started to work at Columbia, actually I started to get into the psychiatry. The questions I have been working on during that time is a neuropsychiatric disease, schizophrenia, okay? And the questions when I started to work on this, the brain disorders, these days I also work on Alzheimer's and this kind of disease, neurodegenerative disease, and also trauma. And actually, you will figure out, actually, for most brain disorders, like Alzheimer's, and also schizophrenia, are highly heritable disease, okay? And genetic can account for around 50% or even more on that. That's the reason, actually, I modified this kinds of path diagram from one of my friends. It's basically we go from the genes to molecules to cells and to the brain, okay? This is the way basically for all these kinds of different kinds of the component, you can use the imaging to acquire a certain type of data to investigate the function and the structure and the function of these different components. And until you have the clinical behaviors, okay? And also confounded with the environmental and the social and psychological factors. Okay, that's basically all kinds of the applications in my mind. I think it's related, all my grants funded by NIH. Okay. Essentially, the idea is basically we wanted to understand these path diagrams. And actually, in practice, there's no single data set to cover all these kinds of the different boxes, okay? And actually, over the last 20 years, I understand them more because I analyze more data sets. And actually, the last several years, I emphasize these kinds of causal genetic imaging clinical pathways, okay? I have all these kinds of different components. I try to set up these kinds of causal pathways. And actually, this causal pathways is a kind of, I call it as a spatial temporal causal pathways to characterize etiology of different brain-related diseases. And essentially, you think about this kinds of changing across the times. And the different subjects, even though they have slightly different pathways, but actually they have kinds of the common pattern behind it. That's some of these question applications during my own research in the field, okay? And actually, as a statistician, and actually when you have all these kinds of data related to these kinds of the big, applications, you dream higher, right? And the question is, what kind of statistical method you can develop? Actually, there's multiple kinds of the tools and the theories for brain-related research. And here I just highlight, one of my students highlight, this first one is multiple biobank and clinical trial data integrations. Another thing is basically omic data integrations. And the third one is the new computational tools to really integrate all the data, different data type, and also the data across the different studies. The last one, advanced method for dense signals. Okay, this is the kinds of the methodology challenges my student outlines in his dissertation. And actually, there's more important statistical topics or problems you can basically, and actually in one of our recent review papers, we review some of these kinds of key topics, and you can take a close look at the areas. And I didn't discuss actually the two topics in my review paper. One is a knowledge-based method, another one is a reinforced learning method, because we don't have too much results in this topic. But in generally, this topic is pretty open to the field and to all the statisticians. And if you are really jumping, I think this is a great time for you to start it. Okay. The main reason is because we have tons of data these days. Okay. You can do a lot in this topic. Okay. And besides basically the traditional statistical topics, and also we think about these days related to AI, we think about interpretabilities, and also think about the general abilities, the data privacies, unbalanced data, and the large language models. Okay. And I just show you what I did. Actually, in the last 5 to 10 years, and this is one of the table I covered from my grant, my recent R1s. And actually, I go to the literatures and also public domains to get all kinds of data back. Okay? And my current data sheet is much longer than this. Okay? But this is still very complicated. It's also related to Alzheimer's disease. Okay? You have also different data types and also people from different background and also different data, sample size. Okay? And also different designs. Okay? And actually, I wanted to emphasize the importance of UK biobank data studies. This is one of the most valuable data set, and actually I'm one of the earlier users for this data set, okay? I think through my career, one of the most wise investment I did in my career is basically I started earlier on this data set. I use this data set basically, there's all kinds of different data types. I never touched it before, I never even know the names. And actually I started earlier basically, invested some resources basically to develop the pipelines and to process all different data, integrate the data together. Okay. And this is very important data, still is very important these days because it's really valuable for statistical community to work on this data set. There's a lot of things can be done in these areas, okay? And this is basically, this is one of my recent papers I haven't submitted yet. It's almost finished. Actually, we tried to develop both data processing method and also data modeling strategies, okay? And actually, you know that, and there's all kinds of data types in this data set. I use this data set to basically train my students, train myself, okay? And for different data types, and also these have a different data resources like inpatient data, self-report, primary cares, and also all kinds of the data, and all kinds of the problems inside how to deal with this kinds of problems. I use UK Biobank to train my students to do it. This is the 1 year job for my students just work on this, okay? After basically finishing the data pre-processing, then we do data modeling. There's all kinds of modeling we need to do on this, okay? And this is basically my student whole year work, 4 of my students work on this. And the first things, some concrete project, or this is one of the projects that we're working on is basically refine the existing imaging analysis pipelines. I don't have so much enough resources to refine all these pipelines, but for some of these kinds of pipelines, I can do it because I have good collaborators, not just by myself. I'm not working independently, okay? I have a lot of collaborators on different fields. And this is one of the imaging analysis pipelines we developed, basically for the cardiac imaging, okay? And this is basically for particular models. This is the concrete models in pre-processing pipelines, and also these modeling strategies we used, and also the disease diagnosis and risk assessment, and also post analysis for basically the whole pipelines. Because for the UK Biobank and actually the ICD-10 code, we generated these kinds of fake code, and then we basically develop these the pipelines to process all the data, to develop the predictive models for all more than 1,000 fake codes. Okay. And this is one of the Professor Feng's results after his colleague sent me some of these their findings by using UK Biobank and other data set. And actually, one thing I'm doing these days is I'm not just processing the data. I do a lot of clinical papers these days. I find that there are some interesting scientific questions. I just pick the data and do the data analysis, okay? Nothing fancy. I just do real data analysis. I write this up, okay? I train my students how to write these papers and tell them this, you need to think scientifically when you analyze the data, okay? This is something we are also train my students doing. Another thing is basically, this is one of my students' the work. My student, Bingxin Zhao, now at the UPenn, Wharton. And actually, this is one of his science papers. We published 2 science papers in Science. And this is one of his the science papers, try to integrate the heart and the brain together. And we do the GWAS on this, okay? We find a lot of genetic signals on this. And then they show you another thing. After we generate all these kinds of the findings, besides the published the papers in top journals, another thing we are doing these days is basically create these kinds of knowledge portals and to share with the community and to basically on this, okay? We aim to build the best knowledge basis of the imaging genetics. And besides that, actually these days, we try to do this logic graph constructions. And actually, I worked in a tech company for 3 years. One of my main tasks is doing this, okay? And actually, we try to integrate, this is one of the knowledge graph is for Alzheimer's disease. And what we try to do is we build our existing knowledge graph. And actually, this is all kinds of existing knowledge graph. And actually, then besides that, the existing knowledge graph has a lot of noise inside. And we try to integrate more information from the literatures. There's a lot of PDF files. We try to extract the tables, a lot of information from the different tables, abstract, and basically add that one and context features in our knowledge graph. And also, we do a lot of the real data analysis. We integrate all our existing real data results in the knowledge graph. That's what we are doing these days, okay? And we try to reduce the noise in the existing knowledge graph for doing this. And finally, I conclude what I really want to do is very similar to this paper. I review kind of the paper on the foundation model for generalist medical artificial intelligence. The key ideas is basically you have the different data types, okay? From text, audios, imaging, EHR signal, and also the omics and the graphs. That's from this real data, okay? Both from observation and also clinical studies. And also you try to extract information from medical domain knowledge, like the literatures, publications, clinical notes, and knowledge graph. Eventually, at the end, I created this ChatGPT type of tools to summarize the existing results and integrate the information as the prior information to build the better predictive models across the different ethnic groups. And eventually, this one paper in Media Archive, they demonstrate that UK biobank is better than most of the data scientists, okay, from a concrete, specific data set, okay? And this is basically the end of my talk. Thank you.
So because this event has the live stream, so we will use the microphone. Just pass around.
Thanks for the very exciting talk. Then my question is simply about replicability. You did a lot of discoveries and using data to explore different features and structured learning and everything, but you talk about ABC. I like that. Like, you know, application big data and computing. But I think this replicability, maybe duplicability, whatever, that I think is very essential for people to really trust and then to understand and even apply whatever the discoveries you have from this big data. And I don't know if you have any comments about the replicability or, you know, reproducibility.
Yeah, I think that's a great point. I think that this is essentially basically when you really develop all these data analysis analytical tools and build all these models in practice, really use it in the real clinical applications. I think the generalizabilities and reproducibilities are super important. Okay, I agree on that. But here, I didn't emphasize this. Is many. I do mention a little bit about generalizabilities of these results. But I think that's super important. You know.
What do you think about infrastructure to do this work?
No, I think the the infrastructure, actually, you think about when I mentioned about the logic graph, all these kinds of things, and also try to integrate the data from different studies and also across the different ethnic groups. That's essentially my key point is you cannot really trust one single studies for everything, for one particular questions for everything. And that's the reason I integrate the data from different resources for the one of these purposes. And additionally, we mainly carry out additional validation studies for doing that. But actually, for me, I take advantage of AI tools, basically, to help us to better summarize all the existing results. And as basically, that's something I think compared with the before, we don't have a lot of these kinds of powers to do it. I think from statistical perspective, application perspective. I think we can use the ChatGPT for doing this type of thing. We can screen millions of the PDF files these days. Okay.
So related to Peter's comments, I think reproducibility is very extremely important. And because the pharmaceutical companies are responsible for the next development, if the result is not reproducible, we will pay a huge price on this. One of the key things for the reproducibility is we don't understand, in general, how large of the alternative hypothesis, because we tried different models at different steps, and potentially kind of use a random forest or some things, and the alternative hypothesis space could be very, very large. In that case, then you increase the false positive rate. So one thing kind of we do routinely these days is kind of we use similar like a GitHub kind of the approach to record the models and also record the steps. So in that case, we can better estimate and understand how large of the modeling space that can help us to know what the chance of the alternative hypothesis. And also before that, it's also very important is we want to better leverage the biology assumptions. So sometimes we often see the case is we got some result, and people can always interpret the result, but we don't want to kind of regard the result correct or incorrect. We want to avoid kind of this case is before we do the experiment, we ask the biologists what the top tier, second tier hypothesis, and if our result is consistent with that, then we can increase our chance to better understand the true discoveries. But actually, another thing that I want to ask the question is kind of related to whom we talk about. These days, there are a huge amount of data is unlabeled data, and each of the kind of how can we better use this data? One key thing is each label is not equally important. Label some of the images can give us more information. Label another kind of image may give us less information. At the same time, our experts have a limited time. So how can we kind of condition on the limited time the expert time is label the most valuable information and increase our chance of the better understanding of this data? What do you think about this?
Yeah, I think this is super important. I think this is emphasized in the second part. I emphasize there's the limited progress in the medical science in general to have this high, large-scale annotated data set. And besides the experts, the limited resources on that, I think the method itself, I didn't see a lot of progress in the field. I think there's much more things should be done on this topic. It's very important in practice.
Very nice talk, thanks.
Thank you.
Too. And actually, my question is very related to that replicability. I think in your talk, one thing missing is hospital, clinical application. I don't care replications, basically. If clinically, that's a real final proof to whatever you said here. For example, your brain disorder or your Alzheimer's disease. If you can find some biomarkers which is really useful for clinical application, I think that's a final proof for your replication or whatever. So I think that's something missing in your talk, or I don't know what's in your mind.
I think
for the final end user.
I think I can completely agree with you on this aspect. I didn't discuss these kinds of the drug discoveries and also validation in the clinical trials. These are very super important things because my theme is focused on medical image analysis. I think the other speakers will cover this topic, and I think I need to even you to discuss that. I think that's basically That's end of my talk. Thank you.
Oh. I just wanted to ask a question. Oh, sorry. Just a last question. So you mentioned generative models. I was wondering what would be the impact on imaging, medical imaging application from these generative models? Because we have more and more generated data. Like everyone is using AI tools to generate data. So imagine if you generate medical images from this ChatGPT, Midjourney, whatever. So what are the threats to these applications? Like if I start, if I can simulate more data so I can improve my model, but what if this model does not align with the medical application?
I think the main kind of barriers is, I think, even though there's a lot of research ongoing on this, but for medical research, there are a lot of kind of regulation, how to use it properly, in what sense, and also how to validate this diffusion model, this type of generative models. And at least for writing the papers published in the AI conference, it's a different story than when you really go to the applications, you really develop the kinds of tools for, for the physicians and for the patients. I don't think that's reached the level yet. I think the whole biomedical image analysis is a totally different computer vision is because of that. Because you don't have a lot of data, annotated data, good data set.
Okay. Thanks.
Thank you. So now we are proceeding to 4 lightning talk for this theme. So the first one is my honor to introduce one of our local faculty from MBZUAI, Dr. Yaqub Mohammed. He's associate professor of computer vision, and he has teaching today. He made his time available to attend this workshop, so I'm very grateful. And his research is very relevant to our theme today, is on AI in healthcare applied to problem in medical image analysis.
Thank you very much. Do you have a clicker here? Yes. Okay, so while we're loading the presentation, so good morning, everyone. Welcome to MBZUAI. So I'm an associate professor here, so welcome everyone to MBZ. I think, I hope that you're enjoying the day so far and the great weather in January here. So great talk before me. Professor Zhao mentioned a lot of things. When it comes to healthcare, there are so many challenges, at least I see in my opinion. I was going to ask a question. What about that clinical knowledge, that how do you feed it into these models? Yeah, not yet. So we talk to clinicians, I talk to clinicians almost on a daily basis to try to fix how these models that we develop work. Sometimes it does work on some population, it fails on others. So there's so many challenges that we still face, and I think we still have a lot more to do to improve what we do when it comes to modeling healthcare data. Okay. So while they're loading this one, so I work in AI in healthcare, and in the past 18 years I've been doing that. So I did my PhD in fetal health, then followed by several years of work on ultrasound images. Then when I moved in here to MBZUAI, I lead the, we're good? Can you just click on the presentation? There you go. Yeah, there you go. Thank you. So what I do is, so I lead a team of roughly 30-ish people to work on a diverse range of problems. The majority of the projects are on medical imaging, a little bit of the projects on non-imaging, but in general, the problems that I focus on are on first, fetal and maternal health, second, cardiovascular problems, and then oncology problems. So I work on not a lot, but probably 2 or 3 different cancers. And then the third part is on pulmonary diseases. In general, these are the clinical problems, but I focus also on the technical aspects. So my team and I try to understand the generalizability, reproducibility of these models, the generation, so the diffusion models and how you can generate data from data. That's when it comes to healthcare, it's much more complicated, and so on and so forth. A little bit of my team work on non-imaging data, and I'll touch on that later on. So before I put these slides, and I know it's a lightning talk, so I just thought, okay, what shall I present? I don't know the audience very well, so I thought, okay, I'll just make it very high level. First, I'll give you a glimpse of what we do in the group, and then I'll talk about a concept that I always ask myself about. Okay, currently, everyone in my domain, we use deep learning to analyze medical imaging. So the one question I always have, what about classical statistical model? Do you still need it? Is this like really deep learning will just fix everything for us? We just put data and get answers. So that's a question I'll try to talk about today. I don't have an answer to it. I have some thoughts, which I'll share with you. And the other thing I thought I'll tell you about is one project where deep learning didn't work. It did not work, and even with lots of data. Okay, if this works. Stuck here as well. There you go. Okay, now it's working. Okay, so this is thanks to all my team members who are working hard on many different problems. And if you're interested, you can find our website. My team and I, the group name is called Biomedia from Biomedical Image Analysis. I did mention this slide where my team and I focus on different aspects of healthcare, from fetal to cardiovascular to brain to pulmonary and so on and so forth. From non-imaging problems, so we work on a small number of problems such as electronic health records. Sorry about the format. It doesn't seem to be loaded the same way that it loads on my computer, at least. So electronic health record is a big thing that we work on, where we have data coming from patients. They're not imaging, but they're just diagnostics, lab results, so on and so forth. The question is, how could we use it? And I would say in the last 3 years only I started to look into this. Before that, I was only imaging person. But that was really probably naive of me, because there's so much information in the history of the patient that can change how the modeling imaging data could be significantly impacted. Other part of my work focuses also on a bit of genomics, but I'm not going to talk about that today. So the question I always ask myself, I don't have an answer, is deep learning, how does it differ from these statistical classical methods? I'll tell you an example. When I did my PhD, I spent so many years in doing feature engineering to ensure that I extract enough features, good features, that when I feed it to random forest or SVM or even basic logistic regression, I get good results. And I would say most of my PhD was on really the data analysis, as Professor Zhao mentioned. We spent a long time doing that. And then I finished my PhD, thankfully, but then deep learning came to the equation. And I was a postdoc at that time, and then my supervisor said, can you repeat one experiment of what you did in your PhD with AlexNet at that time? And I put some data in, and I remember from my PhD, well, the best result I got was probably 81 from a random forest model with lots of feature engineering. And then I put it in AlexNet at that time, and I got 91. So a 10% jump. I was very sad. I was very sad. 3 years of working hard, and then within a week, I managed to get a much better result. And I did publish that in great places, but still, this is what deep learning, I hated it at the beginning, but now we're all working with deep learning. So it is a deep learning model, a statistical model. So we know, for instance, the CNN generates a probability if we're doing classification, but that's not a really a density function. It's just a softmax that generates probability. So the question I always ask myself, is it part or not part of statistics? And the other question is that, what about the other methods? What about SVM, random forest, logistic regression, and feeding that into deep learning? Does that make these deep learning model better or maybe more explainable, because it's really hard to explain what's inside the box? And then I kept on looking into that. So for instance, this is a slide, a figure from a book that just tries to say where everything in the equation. You might agree or disagree with this. I do disagree a little bit with that. But if you look at it, it just puts statistics on the side, while you see other things like deep learning within machine learning, within neural network, and so on and so forth. And there's no proper overlap. I looked into other sources. This is not the source that I disagree with this one, but I put it here to question your mind. So the overlap is different in my opinion, but I want to put that in because there's so many arguments, I would say, between what is statistics when it comes to compare to deep learning and neural networks. So to me, if I want to redraw this one, I would probably expand that orange box and just keep it to overlap with even all the way to deep learning, but not completely within deep learning, but at least a good part of it. Okay, so what is medical imaging? Professor Zhao mentioned that a lot. In general, it's data that we acquire to get access to look inside our human body. So this is, for instance, a human brain and it's an image, it's a 2D slice coming from a 3D image, and each point is a pixel that has a value, right? So why is it complicated? Why is it different than natural images? There's so many reasons, and Professor Zhao mentioned a few. For instance, we work with multimodality data. So if a patient comes in today for a problem in the brain, you're likely to start with a CT scan. It's cheap compared to MRI, fast. It has some radiation, it has advantages, disadvantages. Didn't work, you didn't see the problem, you probably go for maybe CT angiography if there is a problem, leakage in the brain or rupture. If that doesn't work, there will be MRI or maybe MRI before, depending on the condition. So in healthcare, there's so many different imaging modalities, which makes it very complicated when you assess a person's disease. So that's one thing. But the other thing is, it's not just a 2D image. It could be 2D, 3D, 4D, so on. I worked in many different types of data, and sometimes even 1D, if you want to consider ECG. It's not imaging, but it's also a very important modality that we work with when it comes to healthcare problems. So let me ask you this question. What is that? What do you think that image is? I'll just give you a hint. It's two images of part of the human body looking from two different perspectives. What do you think this is? Spine. So, and what is it actually looking at? There's a bright region right near the spine, right? What is that? That's a tumor. And that's what we call the head and neck cancer. What's this imaging modality called? Do you know? Anyone? It's a PET scan. PET scan usually is a type of scan where you inject a radio tracer into a human body, and because that radio tracer is sort of like sugary, abnormal tissue will observe that, and then when you image the patient, you will see that abnormal regions. Anyway, so the real image from CT is that one. You can now really see the brain and the spine and so on and so forth. So the top one is a CT, the bottom one is a PET. To verify head and neck cancer, if I'm a doctor, I need to get these two scans. These are 3D scans, by the way. They're not 2D. I'm just showing 2D here. So why do they do that? Because they want to look at the cancer, quantify it, measure it, stage it, because all these decisions or all these metrics help the doctor make decisions. What are the right treatment plans? Shall I say stage 1 or stage 2 or stage 3, and so on and so forth. So we did a set of studies on head and neck cancer. That's why I picked this study, because we did a lot of publication on this domain, where one major question we try to answer is a patient comes in today to the doctor. Doctor looks at this data. One question a patient will always have, especially in late stages of cancer: what's going to happen to me? Am I going to die in 6 months or 1 year or maybe 10 years? So survival. And that's a regression problem for us. Like if we have data, we can regress for that. But it's not really an easy task. So the reason I put that in is I want to mention our work. We started in 2020 and then all the way until now. And we were looking mostly on, could you look at imaging data alongside electronic health record and other type of data for patients with cancer and tell what is the survival rate? When will this patient die, in other words? So it's a tricky question because you have data, but how could you do that? So we looked into first, let's use the imaging data. See, that doesn't work, it does work. And see if we can use PET and CT and just predict what's the next probability of death. And that didn't work. Imaging data doesn't actually give you good enough information about that. PET gives you, CT doesn't give you much. But then when we augment that with electronic health record, some basic information about this patient, then things started to work. But the other question we wanted to do is we want to work on deep learning, but these sort of electronic health record, because if you put them in a deep learning architecture, it doesn't work very well. You have to really understand what data you're working with. So what I'm trying to tell you here is that in my opinion, the best solution that we managed to bring is to develop a hybrid model that uses classical machine learning with a deep learning model to be able to analyze multimodal data, imaging and non-imaging data. So in this scenario, it was like just a CNN at the top and Cox hazard proportion model, both fed into, if you look at the top part, is also the outcome of the CNN. We did not send it to a softmax, but we send it to a multitask logistic regression. And we found that to be a better approach than just do a basic regression loss function, like a mean square error or something like that. So what I'm trying to tell you here, let me just show you also the video, is for problems such as survival prediction, a hybrid model that uses classical statistical method and maybe a deep learning method that focuses on the images is likely to work better than just using either, each one of them separately. So that's the tumor in 3D. So we extended this work, and Nu'man is here, is my postdoc working with me on this. We published a few papers on that. This is a 2022 papers in MBZUAI where we saw, okay, now let's do something more things. Let's do what the doctor do. The doctor actually looks at the data, quantify the tumor, measure it, quantify some metrics out of it, and then based on that, make a decision. What's the likelihood of death? What's the likelihood of recall of the cancer, and so on and so forth. It's a complicated figure, but what I want to show here that we only managed to get to really good results on multimodal data when we start to augment classical statistical methods with these deep learning methods. Here we see this, we change the CNN to a transformer, and then we still use MTLR to be able to do segmentation and as well as regression. Okay, I'm just conscious of the time. That's why I'm going to close up here with a few questions rather than, so I call it take-home message, but I left it as questions for you. So the first question is on these deep learning models. Which one is better? Which one shall I use? Is it a hybrid model that we'll be using? In my opinion, it depends on the problem. So if we're doing just image segmentation, it turns out there's these deep learning methods starting from UNIT all the way to more advanced version, but UNIT is probably still the most powerful, very powerful method. These things will work well on imaging. But when you start to have multimodal data, really, just basic deep learning model may not be the best option. In fact, for some problems, it's an overkill. I don't have a slide for that, but we're working on Alzheimer's disease on a study where we actually showed just analyzing the MRI directly doesn't help. We have electronic health data. So what we did is we get the segmentation masks of the different structure of the brain, but then we compute radiomics features, some basic features. Then we feed that to just methods such as boosting or XGBoost or other method, and it works as good as, even better in some cases, than deep learning models. And the last question is that, this is what I just mentioned, is like, do we really need to learn from images directly, feed it into a CNN or a deep learning model? In my opinion, in some cases, yes, in some cases, no. So you have to understand your data before you make that decision. And with that, I'll finish. Oops. Sorry. And thank you very much. I'm not sure if we have time for questions.
I think we have time to take one or two questions.
I can shout.
Yeah.
How are you getting measures of uncertainty? How are you calculating? I love your hybrid model. I think it's fantastic. Personally, I think it's great. But how do you think about uncertainty and talking about the uncertainty to your partners,
Yeah.
like the healthcare?
It's a very good question. We study that as well. Like how do you estimate uncertainty when you make a decision? So there are different ways you can measure that, but currently what we're doing is we're looking into, when you have a tumor that you want to segment, and the deep learning models or the algorithm is giving you segmentation. We're studying that in the sense where you have multiple doctors already segmented the tumor and try to measure the deviation from each one to come up with methods. So the best way we do it now is simply by understanding how doctors are different. Because uncertainty is also, so it comes in healthcare, it comes under subjectivity as well. Because if I ask, in the head and neck cancer, I think we did a study on that, but I don't have the numbers. But let me give you another number. In segmenting brain structures, a brain tumor, doctors will actually agree on approximately 80% of the time, if you bring two fantastic doctors. So there is already subjectivity in segmenting or figuring out where the tumor is. So we follow similar attitude, similar paradigm where we have data where we have multiple annotators, and we try to measure their uncertainty. And we say, if this deep learning model is actually within the bounds of two humans, two experts, then we're good. Otherwise, we're not.
I don't know this cancer very well, but my first question is that why there's no treatment? When the cancer is diagnosed, and then the first thing a medical doctor will make a decision on is come up with the right treatment, is radiation, surgery, or something. Why this information is missing in the prediction model? I mean, I know that you mentioned a few like demographic model or clinical variables, but I think the treatment or this cancer cannot be treated. I have very limited understanding about this cancer.
So
but anyway.
The question is why treatment is not included when you train
Right, I
these
think
models.
that will be a very important driving factor for survival.
I agree with you in the sense that depends the question that we're trying to answer. Here the question we're trying to answer, could you do that? Could you predict survival just right when you get the data before any intervention happens? So this data that we worked with doesn't have, all the images has been acquired before any treatment. Okay? So that's where we want to answer. Once, I agree with you, if you have this sort of data after specific treatment, feeding that to a model, that will be a better approach.
Yeah, so just curious, for the AUC then, have you compared with other well-known markers for head and neck cancer, for example, HPV status, positive and negative? So I'm just wondering how much does PET scan add to the markers that are currently used in the clinic?
So I don't have a specific number to answer that, but we know that PET scan adds significant help to the doctor to make sure they can quantify the cancer. From the CT alone, you cannot really see the cancer much. And the other thing that PET scan adds significant help is that lymph nodes. So, you know, when the cancer is spread to lymph nodes, it becomes very tricky to see it on any imaging modality except the PET scan. So I don't have that number, but we know that it's a clinical standard that if a patient comes with a head and neck cancer, they go for a PET CT scan. It's, by the way, it's now, with the current technology, it's one scanner. It gives you classical information, and it's quick to do, and so on and so forth. But as a next stage, you go for that. It's similar like what we do like in prostate cancer. You do prostate cancer, you do blood test to measure the antigen, prostate antigen, PSA, and then but that we know it has it's not really very specific. It has 75% false positives. So what they do after that is to go for MRIT2. So we know imaging usually give you a much either more specific or sensitive, depending on if we know PSA is great, but it's really give you lots of false positive, and many people end up having biopsy for no reason.
Yeah, I just quickly want to follow up Peter's questions. So predict the patient survival is interesting, but ultimately we want to understand what we can do for this patient.
True.
The predictions and the variable features for the intervention, that's very different things. So have you ever done some work? What the treatment can better helping this patient?
No, that's a very good point. No, we haven't done that, but ultimately you want to use this information to help with the improving the outcomes later on. So my team and I, we didn't touch into this yet. Hopefully in future. Okay. Thank you very much, everyone. Thank you.
I know that you need to go teaching, so thank you so much for. Okay. So our professor of biostatistics at University of Michigan. His research focused on the development of statistical method motivated by biomedical application with a focus on neuroimaging.
It's fine. Still works. It's okay. Just leave it and turn it on.
It's on?
Yeah.
So, okay, good. All right, yeah.
Is your clicker?
Okay, thank you. Yeah, so, yeah, it's good to learn this high-tech knowledge, this AI field, AI area. So, yeah, so thanks, Tian and Hong to organize this workshop and invite me, and thanks MBZUAI support this event. And today I'm going to share some my understanding of like my naive understanding of deep neural network for imaging data analysis. So as I'm training as a statistician, I didn't learn quite a while about the AI or machine learning algorithm during my PhD studies, but later this area, everybody talks this area. This is a very exciting area, and it works very well in many applications. And now I began to try to understand and kind of take some effort to study this method in my field, the neuroimaging studies. So basically, I think Hong Tu gave a very nice overview of the entire medical imaging field. What I'm talking about here is a little bit narrow and only focused on brain imaging application. And here is some like a common goals in brain imaging study, like activation study, which is related to imaging segmentation problem, but is particular for brain activation. So, and also co-activation or connectivity studies, and also in neuroimaging, there's prediction classification problems, and I have been doing some meta-analysis, and recently we are doing some multimodal imaging, integrate different type of brain imaging. And so I think I have learned since my PhD study, so it's important to start from application to analyze data, and also important to start from simple model, simple things. You try very simple model to a data set, see what's going on, and then whether there's needs to make it complicated, right? So this is something like regression analysis or linear regression as the most powerful kind of statistical models I have learned so far, and I'll try a lot of like a data set, a linear model actually works reasonably well, and of course not necessarily the best model, but it always works. And in imaging application, I primarily work on several type of regression, like image on scalar regression, or scalar on image regression, or image on image regression. So basically it depends on you put the image as a response variable or as a predictor variable, or both. So, and they actually have a different goal to try to understand different kind of like brain activity or different aspect of the brain imaging research. So, but here I try to maybe give some answer to Jakob's questions about deep neural network or deep learning is a statistical method, or which model we should to use. So actually we try both like linear model, and if you using deep neural network in this type of regression, what's going on. So this is some our recent effort. So well, the first one is this like a image response regression. So if you put image as response, and you put all the scalar covariates, scalar variables as covariates, so can we this is actually quite a simple model that you can apply linear regression by each location of the brain, and then you can get this so-called massive univariate analysis. Then you can actually get an estimation of the parameter. And the idea here is that because the signal-to-noise ratio is relatively low, and there's a heterogeneity among the subjects and the data set. I mean, traditional neuroimaging studies, the number of subjects is relatively small. But nowadays, they have increased a lot. But compared with the resolution of the image, like thousands, hundreds of thousands of voxels in the brain, that sample size is still relatively small. It's not like computer vision kind of sample size. So in this case, we're trying to bring in the deep neural network to model the spatial invariant coefficient in this type of the model, and we gain some like very interesting results that basically, if you compare with the traditional statistical method, like a non-parametric method, like a kernel method, like a spline, and other like non-parametric regression type of method, like low-rank approximation with sparsity. So those all methods just handle this type of like this is a kind of simulation study. Like you can see that from the very basic method, like the massive univariate method, and this simple linear regression. And if you do kernel method, this is panel B. And if you do the low-rank approximation, where if you do some smoothing after linear regression, where you do spline, and they compare with deep neural network, actually deep neural network can do almost perfectly recover the true signal. And this is actually not a quite easy design, because we try to have a sparsity on the true signal first, and also we have a very high level subject level heterogeneity. So when you observe the data is quite noisy, and also the spatially adaptive, like smoothing, are quite different across different locations. If you want one simple traditional statistical method actually cannot achieve like to recover this very well. So, and this is the sort of powerful of the deep neural network. Here, one special like using deep neural network, you can design the output layer using thresholding, like a kind of activation function, then you don't even need to use any shrinkage method like a penalization method. You can achieve sparsity, exactly sparsity, and then you can avoid to use like all type of regularization method in the model feeding. And we actually have the theory show that it works well, at least for this image response regression. And another kind of effort we have made to try to simplify the deep neural network for the particular images, scalar image regression model. So the idea here is that because we know some like brain structure and location informations, whether we can just simply build in that information into deep neural network, and even we don't need to go very deep. We actually start from just single layer neural network. So everybody familiar with neural network theory, that is that one layer single layer neural network actually has uniform approximation theory, that you actually can recover any continuous functions in arbitrary accuracy. But basically the number of the nodes in the layer is important here. But here we're trying to bring in the brain structure information, and we can actually achieve much better performance and compare with like a state-of-art, like a convolutional neural network method. So basically, there's some opportunity if we incorporate neural imaging like prior knowledge, like a brain prior knowledge, you can actually simplify the neural network and actually achieve quite comparable results compared with state-of-art like a convolutional neural network. And another effort we are recently trying to kind of integrate the deep neural network with some other machine learning method like Gaussian process or SVM. So this is something like we build up the some important parameters like kernel parameters in the the Gaussian process, and we actually using deep neural network to construct the kernel instead of like a directly apply deep neural network. So that actually can achieve better interpretability, and this is a very complicated task that you use one set of the neural imaging. In this application, we motivated by using resting state fMRI to predict task fMRI, and we actually can handle a very large dimension of the input and both the predictor image and our response image, and also they not necessarily in the same imaging space, and they can be very flexible. And if you kind of combine the deep neural network with the Gaussian process, you actually can achieve much better performance. Here is one example that we can identify which part of brain is sort of predictable, and if you compare with like a regular voxel by voxel image on image regression, or like a just simple linear regression, and the original paper from Science to address this topic is based on this linear regression problem. Then they cannot find any region of the brain actually predictable. But based on this new method, we actually can identify quite a few regions of the brain are predictable from the resting state fMRI to the task fMRI. So this is a 3 example I want to share here. That basically my view of the deep neural networks is my naive view. It's definitely part of the statistical model. So and it's actually can be integrated with classical regression model or other statistical models we have been quite familiar with, and it depends on how you actually use it, and it can be simplified or modified for your purpose. It depends on your application. If you quite understand your application very well, you actually can design a kind of like user-specific neural network for you to improve the performance. And if you combine the deep neural network with other machine learning tools, you actually can boost the power. Depends on how you do it. And there are some research topics I'm quite interested in right now. One is how you using deep learning to help you do the experimental design. I have been working on one application like brain-computer interface that you actually can design using machine learning algorithm help you to design to collect data by yourself. I think it's important that we know how to do the image acquisition, and then we can collect the data by ourselves. Then we can better actually do the analysis. So I think a lot of like a data set is not, if it's not collected as what we expected, we need to do a lot of effort later to actually find a signal. But if you collect it correctly, then it's very easier to you to find a signal. So I think other important topic, like in my view, is like a manifold learning, with instead of like do the voxel-wise selection in the neural imaging, you summarize the signal globally from the brain. That's important. That's a part of manifold learning, and also we are doing some data integration and causal inference. And another important topic we recently start to work on is prediction uncertainty quantification. So I'm trying to understand whether this problem is predictable using the given set of the predictable. So how you define predictability. So how you actually can define formal statistical measure to measure on that. And also we want to, so you think about the prediction actually can be very hard, it can be very easy. For example, I can predict in the next second, everyone's gonna sit here. No one stand up. Yeah, this prediction 100% correct, but I cannot predict in the next hour, everyone still sit here. Right, so this is going to be quite different things. So it depends on how you measure that and how you actually formulate the problem. So, and I think in this area, there are kind of promising AI techniques like a large language model and generative model, especially for the imaging related, computer vision related generative model, and reinforcement learning like deep Q network is very popular and useful for the experimental design problem, and also transfer learning has been very useful for the data integration. So there are some very important issues. I think Hongdu already addressed most of them. I think I think we need a scalable and affordable computation from both hardware from perspective, also like the students need to know how to programming very efficiently. I think from statistical or biostatistics department, their programming has improved a lot, but I think not comparable with computer science people. So it's still like that's a major barrier of our implementation of the ideas and research. And also I think I hope we can have like ImageNet-based like medical imaging for a large database, but it's very hard, as Hongdu mentioned, a few challenges here. And also, I'm very interested to see all your opinions about theory development. I think Hongdu mentioned that a little bit. So should we shift our theory development a way, or not necessarily a way, or at least in addition to the traditional statistical model asymptoticals. So what type of theory we should look at for this new model involved deep neural networks? And I think this whole process is a learning process for myself, and I think we have to keep learning and also think about what's the best strategy training next generation of statisticians. That's all my thought here. Thank you.
Jay, great talk. I think for me, for most of the regression problems, I would be just use pre-trained models from the CV, like foundation models, and basically as a building block for the traditional statistics. I think they should be performed much faster than you train the model from scratch.
Do you mean the CNN or?
No, this is the IN, all these kinds. They have a lot of different the pre-trained models based on the existing data sets. Because that's just like you dump your imaging data, your medical imaging data, and you get all the features, and then using traditional models to do everything afterwards.
Okay.
Because without basically you train the model from the scratch. But you're kind of most of the
so
models.
So it's more like the transfer learning part of type of.
Not transfer learning. It's more like you dump the imaging data into the neural network, the existing trained models, because you know all the weights and the hierarchical the architectures. You just kind of transfer the data to another dimensions and do all the traditional statistics.
Yeah.
That's one of the key reasons they try to build these foundation models, and for different applications. Then that's the make this feasible in practice. In like app, they can easily do it in practice without basically build everything from scratch.
Yeah. Thank you.
Great talk. So quick question. So what is the major bottleneck for building the large database for medical imaging? What do you guys think?
Yeah, I think there's a very complicated pre-processing steps there's I think for different type of the imaging, and also for different experimenting sites collecting the imaging, they have different machine and different acquisition procedures, and also there's some issue about the sharing data.
Sorry. So in my applications and collaborative projects, I work a lot of other type of imaging data. For example, dental imaging, where we study our health from kids and trying to find some our diseases, by looking at imaging data. And also we look at some wound size from diabetes patients. That when patients have a severe diabetes, they start have a lot of the wounds and ulcers on the foot, so that they may need to go through the surgeries like amputation or something like that. So I don't know, when you work on all the imaging data, whether or not those deep learning or whatever segregation algorithm could be applied to other imaging data. I know that the brain imaging is very challenging, it's very sophisticated, but I wonder, for my sort of applications, I say whether or not your method can be applied, or you have whatever method developed can be applied to other type of imaging, so we don't need to develop our own method to deal with our imaging data. Do you have this generability or applicability of your method to other fields? I hope that when you write a paper, you can use different type of imaging to show the generability, so that we can use your method to our field.
Yeah, I think that's a very good point. So the current method we develop, I think for the image-on-image regression, we can do that. So for any type of the imaging, not necessarily the neural imaging. So any medical imaging, as long as we can use deep neural network to regenerate that image. So if you can regenerate that image, and then we can actually build up the method to do prediction and also to do the model fitting. And for the first project, that is a very, very simple idea to apply neural network. That require you have to register image in the same template, same space. In that case, maybe other type of image not necessarily applicable here. But I think the power of the neural image, the power of the deep neural network type of the method include those generative models. They can actually fit any type of image, even they are not registered very well. And in that sense, you can actually project the image into lower dimensional space like latent vector space, and then you can to align them in a lower dimensional space, and then you can do the regression model. Yeah, that's potentially definitely, but that quite depends on the specific applications.
So I'm curious because you also mentioned that now there are many generative models, right? Can help to generate. Then is your model good enough to generate a lot of medical images that represent? Then we do the segmentation on the generated. Why do you still need actual? If your task is like segmentation, why would you still need real images?
So the generative model is more like can be used to represent the observed image. So you can generate the image quite similar to observed image, and then in that model, if you can kind of extract a useful feature from the generative model, you can actually get those parameters and using those parameters to do the subsequent analysis. Basically, that's the idea. So just like a large language model, you can generate a lot of words and sentences to represent some ideas, but there are some key parameters and the structure in the model can be used those parameters can be used to build up the latent structure regression later.
Yeah. Yeah. So regarding uncertainty quantification, so can you give specific examples in your applications? Is it just the dimensionality of your image that makes the problem challenging, or is there something more specific to this application?
Yeah, it's a very specific, so in this example that we're trying to kind of look at at which location of the brain actually your social, language task of the brain activity can be predicted by the just resting state of brain activity. So in that case, we want to identify which part of brain actually quite related to that. So in this case, you can see this is not an exact uncertainty quantification. It's based on our kind of empirical results to see the predictive R-square. So you can see in some of the brain, like front lobe, you can be quite a while predicted. So in that case, our goal here is not show this is given the data, whether we can actually predict, give the measure of each location, whether this location can be predicted or not predicted.
So it's like a prediction interval for a pixel or like something?
Right. Yeah, you can construct prediction interval. That would be one measure you can consider. Yeah.
Thank you.
Yeah. All right. Thank you.
Our next speaker is Professor Martin Lindquist, who is a professor of biostatistics at Johns Hopkins University. His work focuses on mathematical and statistical problems relating to neuroimaging with a particular focus on fMRI.
Thank you. You can hear me, right? Yeah. Thank you, Tian, and thank you, Hongtu, for organizing. Thank you, Philip and crew, for all your help as well. It's been really great so far. So when I was thinking about my lightning talk, I asked Hongtu, what should I talk about? And he gave me 4 questions. And being a very literal guy, I took those 4 questions and made 4 slides, each answering 1 question. So it's going to be very different from the other ones. No fancy images or equations, just maybe sort of high-level thoughts about these 4 questions. Let's see here. The suspense is killing us, right? What is he going to say about these 4 questions? And what are the 4 questions? Ah. Yeah, these are the 4 questions, by the way. Thank you. So I can just go forward like this. All right, so I'll get to these 4 questions as we move along. But so the first one was really about what would be the next stage of research in this field for the next 5 to 10 years. And so again, my focus is, I do a lot of imaging, but primarily it's neuroimaging, and primarily it's functional neuroimaging. So most of my focus is on that area. I think one of the big things that was happening right now in the field of neuroimaging is sort of the transition to the era of big data. So Hong Tu really nicely talked about that. There's these biobank-sized data sets. It's sort of changing the paradigm. Usually people had 30 subjects if they're lucky, 50 subjects, and they, even if the correlation between some trait and brain volume was, say, 0.15, because it was so few people, the sampling distribution was so wide, so they were getting sort of correlations of 0.9, and that's what Nature and Science decided that you have to have that to publish it. But it's sort of driven by noise. And now that we're getting into these biobank size where there's like 50,000, 100,000 people, you're going to get very reliable correlations of 0.15. So they're going to be smaller, but much more reliable than the ones that we've gotten used to seeing. And sort of that's going to sort of have to change our way of thinking about the problem. And also the sort of statistics that we do has to change with that. And so I think we're in a real paradigm shift. And I think Hong Tu's work is a very nice example of this paradigm shift. It's something that we sort of have to sort of move on. And it's going to create a lot of complications. So I'm calling this population neuroimaging. The second thing a lot of people talked about is multimodal data fusion, as I call it. That's sort of one of the things I was sort of complaining to Chen yesterday, that we had these 4 sections: EHR, imaging, smart, computational. It's really one, right? At the end of the day, if we're going to do all this AI stuff, we're probably going to combine all that information into one. So we should really be talking and not siloing ourselves artificially. So I hope we try to avoid that. The third thing is, acquiring better images in shorter time. There's radiation doses, there's patient burdens, there's cost. If we can acquire data quicker, easier, that's something that we're going to be looking to do in the coming years. This is, I think, one of the most critical things. Somebody mentioned clinical application. We're very, very bad at clinical applications, particularly in functional neuroimaging. That was the big promise, right? We're going to read the mind. We're going to understand everything that's going on. It's not that easy, right? And moving from sort of our studies of 30 people in our papers and moving it into the clinic is a huge endeavor. And I'm going to be a little critical of us a little later on and say some of these things. Understanding individual differences. My brain works different than your brain, right? It's just the way it is. And there's very subtle differences, and sort of understanding that is going to be a complex thing moving forward. And again, as John said, brain-computer interfaces and the like are big things. So that's sort of where we're moving towards. I really think this big data, population neuroimaging, fusing data types, and trying to get more clinical applications are sort of some of the big things that we're looking for. Question number 2 was most exciting and pivotal breakthrough that AI and statistics could change the practice. So I thought a lot about this, and sort of ChatGPT and those things were real game changers. When I saw that, I was like, wow, how can they do this? And I was thinking, what is it that it's really doing? It's synthesizing information, right? And that's something that we kind of do in neuroimaging as well. Again, we often do we have 100 studies of 30 people of working memory, right? And so how do you synthesize that information? Well, people usually do meta-analysis. So they extract tables from all the different PDFs. They look at where the locations are, and then they try to combine this into something. And that's something that ChatGPT could really do, meta-analysis, right? So if you have, it could find the papers, it could extract tables, it can sort of synthesize these information. So you can imagine a future where you could just ask something about these things, and they could perform meta-analysis. And I also think that there's a way of sort of the idea that we're moving forward is sort of querying brain maps. So if you put in a structural map, you can say like, well, what's the amygdala volume in this brain map? And comparing it to sort of population norms and things like that. That's also something that a synthesis of information that I think that we'll be looking at moving forward. You know, you could put in an activation map and try to figure out what it is that this person is doing. Do they feel fear? Are they in pain or whatnot? And so you can imagine lots of those different things moving forward. And so I think synthesis is something that we're going to see a lot of. Data fusion as well. I mean, it could be that we have a bunch of different data sets. So, you know, I'm lucky and I have data types A, B, and C. Tian has A and C. Hong Tu has A and B, right? So we want to sort of combine all that data and sort of borrow strength, even though we don't have the same sort of imaging modalities or even data types. Like you could have genetic information, I don't, but how do we, so it's sort of it's different from a missing data problem, it's a missing data type problem. And I think that's something that one can work with AI, and that's going to become very important as well. And then this was another thing, is sort of, it was a very interesting question, you know, about replicability and things like that. You know, these small studies of 30 people are really great for a lot of things because they're very targeted, right? They're targeted with a very strong research hypothesis. Biobank style data is diffuse, right? There's no targeted, it's just there, right? And so the question is, how, but the biobank data has information. We're humans, right? We're all humans, and our brains have certain properties that are sort of common with each other. So what is it that in the biobank data that we can take that can help inform these more clinically targeted things and help, you know, kind of get more refined estimates in these more targeted estimates. And I think that's going to be sort of one of the big research topics. And I think that's something that statistics, you know, you think sort of like an empirical Bayes thing. You're shrinking towards a population average, but you're really trying to also retain the individuality of the 30 people that you're looking at. But I think that so there's going to be a lot of interesting ways of doing that moving forward. And then also we talked about this, developing synthetic data. So, you know, again, can we do sort of fake brain data that can sort of help do this? It's sort of interesting. People have tried to make fake brain data, but it's kind of hard, right? You can sort of see when it's wrong, because sometimes you do processing of brain data. You take the brain data is like this like folded scrap of paper, right, that you crumpled up, right, because it's all folding. And then you can, if you take that volumetric data and try to synthesize it, you know, there are pre-processing steps where you sort of blow it up afterwards. And then you can really see when it's synthetic, because it can't handle that curvature that exists very well. So it's actually much more complicated in the brain than it is with real images and things like that. And those are the sort of things that we're going to have to sort of figure out how to deal with. So it's a very complicated problem. And then this was sort of a bigger picture thing. Hong Tu says, think big, understanding how we learn, right? So these algorithms are learning, but we're also learning. And a lot of things that we do, it's like, let's say that I'm learning how to circumvent a maze or something like that. I get better and better as I get more information, right? But also my brain is processing it different ways, and sort of understanding how those things go intact, I think, is something that this AI could help a lot with. So those are sort of things I'm sort of keen on. What's the most important research questions? Again, moving it into the clinic. I think if we don't move it into the clinic, you sort of, why? You know, like we're learning a lot about the brain, but at some point we have to sort of, it's public health, right? So this is an interesting thing about, you know, so Joan, you're talking about sort of pre-processing pipelines. There's a million different pre-processing pipelines. You know, the dirty secret is in all these big data things, a lot of the pre-processing is done in sort of a modular fashion, so that you use one software to do this pre-processing, another software to do this pre-processing, a third software to do these pre-processing. those things interact with each other, right? So it could be that the pre-processing you do after the first one sort of reintroduces the effect of the first. Happens all the time. And similarly, analysis techniques can reintroduce artifacts and confounders that you've previously removed. And it's really a really problematic thing. And so that's one of my fears with sort of deep learning, is that you do all this pre-processing, and then the deep learning sort of relearns the artifacts and puts them back in. And there's big artifacts. In imaging, for example, motion is a big artifact, right? So if people move. So let's say that you take away the motion from the artifact, and then you sort of predict who has ADHD and who doesn't. Kids with ADHD move more than others, right? And so motion is a much bigger predictor of ADHD than brain, right? And so what if the algorithm is learning who moved sort of indirectly in very subtle ways, right? Then you're not really learning anything about the brain, right? You're learning things about the kids with ADHD move, right? And that's the wrong. You're getting a prediction accuracy, but it's not about the right thing, right? And so I think we have to be very careful about that. Causation in the brain, that's sort of the holy grail, right? You know, does activation here cause activation there, cause activation there? I think this is prone to a big, you know, there's this sort of transcranial brain stimulation and things like that. That's really sort of promising these days. You can sort of kind of zap an area of the brain and either suppress or activate brain regions. If you think that you have some sort of graph, you can sort of basically manipulate sort of nodes in the graph in ways. But this is an engineering problem as well, to get this data simultaneously as you're doing functional neuroimaging. So a lot of these things are going to be partnerships between analysts, engineers, and sort of domain scientists. And those are things that are very important. Figuring out what AI is useful for. So AI is pretty useful for things like normalization and segmentation. We heard that several times today, right? Why is that the case? Well, they're basically relearning an algorithm, right? So basically, normalization is like all our brains are different sizes, right? But in order to analyze them, we need to make them the same. So you take everyone's brain, and you put it onto a standard template so that all our locations are aligned with each other. This is a warping algorithm. And there's lots of these different warping algorithms, but that's basically what they use. You use the original data, you use the warped data, and deep learning is great at learning that transformation. Perfect. Same with segmentation, right? It's an algorithm that they're learning. So it's great for that. It's really bad at developing biomarkers, right? So like, can you predict Alzheimer's or depression or something like that? It doesn't do better than a linear predictor. Why is that? It's probably due to the sample size. And so there's no point in doing it because you're giving up interpretability, and so you're losing interpretability with no win. And so that's something that we sort of have to figure out, if there's either sort of a data augmentation thing or something like that, but that's a big bottleneck, right? So it's good for learning algorithms. It's bad for learning things that we don't really understand, right? And I think that we have to sort of figure out why that is, because, you know, we always want to use the latest shiny tools, but it's only meaningful to use it if it's giving us some benefits, right? So I think we have to be a little bit careful. Last question. What should we statisticians do to get started and accelerate progress? Here I thought maybe I could be a little bit controversial, you know, since we're all statisticians. We can, you know, one thing is, this is team science. You know, Hong Tu, you know, throws out those things, but analyzing 100,000 people is hard. Yeah, you need software engineers, you need you know, computer scientists. You need teams of people to do that. It's not like a solo thing to do. So you have to get involved with teams. You have to access the data, right? So again, having early access to the biobank is important. Having, you know, you can't just wait for the data to come to you. You have to do that. Understand the data. You know, I think even you said this yesterday. Like, what do they usually say about statisticians? We get to play in everyone's backyard. I would say for the last 10 years. That might not be the case. You know, we can certainly play in everyone's backyard, but we don't make any impact. To make impact, you have to understand the data at a much deeper degree, and you can't dabble in things in the same way. And I think it's dangerous to sort of think that you can do that. It's tempting because you know it's fun to dabble, right? But I think we make our biggest impact when we don't dabble and we focus. So I'm trying to be a little provocative there. And so we have to collaborate across domains. This is hard, right? My best collaborator, you know, I met at Columbia when I was there. We talked he's a psychologist, so we talked for a year. I had no idea what he was talking about. But he was a pleasant guy, so I had coffee with him every week. And so I didn't have very many friends, you know. So it was really nice, you know. But man, I had no idea what he was talking about. And then after a year, I suddenly understood what he was talking about. Now we have 50 papers, right? I mean, so you have to work at it. Get outside your comfort zone. Again, it's not easy talking to people who you don't understand. We're proud, right? We don't want to seem stupid, but you have to be willing to be a little stupid. And then, so this is my last one. I think we do really bad. We don't stick with the problem, right? And so we had this little paper on biomarkers in neuroimaging, and we looked over the literature, 500 studies, and we looked at who actually took their model and then started applying it to sort of independent data sets. 9% of the studies did that. And that's shocking because, and I think this is the problem with getting to the clinic. Like, so what do? We publish a paper in JASA or something like that on predicting Alzheimer's. Once we get our JASA publication, we pat ourselves on the back and we call it a day, right? We don't stick to it. And that's not going to make a biomarker. What's going to make a biomarker is that you then apply that model to data from a different site, on a different population of people. You just have to test the heck out of that model. You have to stress test it until it fails and figure out when does it fail and when it doesn't fail. So there's this whole biomarker development pathway that we largely ignore, right? Because our reward system is to get a publication on this model. Our reward system is not to do all these things, but I think that's the wrong reward system. And I think that, so if I can be a little bit provocative, it's sort of like, it's really nice to make these fancy models, but if we're really going to change the world, we have to get outside of our comfort zone and sort of force the issue, right? Because people are not going to come to us and say, oh, I read this excellent article in JASA. No end user does that. It just doesn't happen, right? We might think it happens, it doesn't, right? So we have to sort of be a part of this and force this issue. So that is my call to this group to do that. And I think that was it. Thank you. Okay. Oh, yes, absolutely. Yes.
Yeah, so of course, you know, I'm in a stat department. Okay. Of course, I'm in a stat department. It's a much worse situation there than in biostat, as you well know. I mean, in terms of actuating 1 through 6.
Sure.
Right. So, what are your thoughts? I would just love to hear other people. You know, our whole utility function is so against 1 through 6. It is unreal. I mean, because I really, you know, I want an annals paper. I want a, you know, or a NeurIPS paper. But to have any kind of impact in real life, I mean, when are we going to get credit? How can you convince your postdoc that they're going to get credit if they actually get a biomarker that might get used? I just would love to hear some conversation about this. It's so frustrating for me.
I'm not saying that I have all the answers here. I think that we're lucky enough to be able to sort of change that. Like I have tenure, I'm comfortable. You know, I can do that, right? Again, the postdoc is harder. I will say I have 2 types of students in general. I have one type of student who basically thinks of the image as a matrix and does good math on it. It's cool. I have another type of student who says, I want to understand this, so I'm going to embed myself in this lab of adolescent health and learn about ADHD and autism and do that. That's cool as well. That later group always does better on the job market because they're different. And so I tell all my students, is like, you might not be comfortable doing that and sitting in this lab, but you're going to do better on the job market, and they do. So I understand what you're saying, but I'm not convinced it's 100% true, because people do like to see someone different, right? And those people are different.
I see why Susan asked the question. I actually did 1 to 5.
You what?
I did 1 to 5.
You did 1 to 5. Oh yeah.
But I didn't ignore number 6.
Mm-hmm.
It's not my fault, because when I talk to I spent like 15 or 20 years with real doctors. Whenever I speak, there's a Herbing's PhD. Okay? so he can publish whatever he likes, but they don't trust what I produced. Okay? I trust they produce, but they don't trust I produce. So that's unfortunately. It's not just get out of comfort zone. There is something going on between MD and PhD. Okay, so it's not actually trivial questions. Whether anybody has the ability to overcome that question or problems will be an interesting part.
Well, if you want me to be really provocative, you should hear my thoughts about MDs.
Okay. Anyway, my other question.
But this is filmed, right? No.
I think Susan expects me to be daydreaming now, so I'm not going to ask a daydreaming question to you. So if somebody give you $10 million for the next 5 years, and you have a team of 20 individuals, what do you like to do?
I missed the last say. I have 220 and...
You have somebody give you $10 million, okay?
Yes.
And for 5 years.
Yeah.
And you can have a team that you don't have enough, you can have 100 people, say, give you 20 people that you can build a team, all right? So what would be your question on imaging analysis related to health improvement, that you actually, a question you feel you can solve and change the field to some extent?
Well, actually, this has happened. So I lead the acute to chronic pain signatures program. It's an NIH program for studying 3,000 people who transition from acute to chronic pain. So we have a longitudinal study studying people who have an acute pain episode, which is a surgery. And of those people, 20 to 25% are going to develop chronic pain, which is that you have a pain of, say, 3 or more on a scale of 10 after 6 months, right? So a lot of them then become opioid misusers because it's hard to live with chronic pain. So understanding that mechanisms is important. So collecting imaging data, 5 different omics types data, EHR data, patient-reported outcomes. So all the things that we're talking about here, how are you going to sort of combine those into some sort of signature for developing who is resilient to chronic pain and who isn't? So what kind of people do you need? You need a lot of people who can, there's a lot of processing, you need software, you need supercomputers, you need software engineers, you need people with domain expertise in each of those fields, because there's so many subtleties involved with EHR data that I don't understand because I don't spend very much time with that, right? So you need all those things, right? And then you can start making a dent in the problem. And you need people who speak different languages. So you need people who sort of speak, a more scientific language, but also a more technical language. And so you have to sort of build on that. I mean, so that's what I do.
So for the interest of time, so thanks for Martin. We need to transition to our last lightning talk of the first session.
Oh, I want it so badly.
Our final lightning talk of the first session is Professor Annie Chu from University of California at Irvine, and she's a professor of statistics. So many of us know Annie's work, and she definitely worked not just on the imaging, but she has done a lot of important work in this theme.
everyone can hear me okay? Okay, thank you, Tian and Hong Tu and many others and all the participants. Also, Philip helped a lot. And actually, I never see any other slides from the other speakers for this session, but I was surprised when you will see we are hitting on the same problems. And I have some answer, but not all the answers. Okay, actually, first, actually, a lot of us talk about imaging, always talk about medical imaging, right? And a lot of medical imaging is about brain medical imaging. Now, why? You have to ask, oh, is it, okay, is it working? Hello? Can you hear me? Is it working?
I think it's working, it's just not very loud. No, it's not very loud. People on Zoom can see.
Oh, the Zoom, they cannot hear. Should I just use that one? Okay, yeah. So actually today, I'm actually talking about some other imaging, but I'm actually starting with this brain imaging. We work on a lot of Alzheimer's disease, right, ADHD, but I think because a lot of us interested about aging and Alzheimer's disease is a very progressing disease. So this kind of imaging, you see PET imagings, you will see the progression of the Alzheimer's disease. I would say this is a very classical medical imaging examples. It's just one of the examples. And usually when you see that, this you can see, oh, we have a shrinking hippocampus and enlarging ventricles, right? This is a kind of indication of the Alzheimer's disease progression. Now, this is traditional statistical analysis of what we're doing: classification, signal detection, involve model selection, spatial statistics, statistical inference. Susan mentioned about the uncertainty, right? Because the statistical inference, we are doing a lot. We answer the question about the uncertainty. But actually, the challenges, right? This is one of the questions. Actually, this also hit on with Martin's question and also Hong Tu's question. We have multi-source of data. Also, people sometimes call multi-modality. We not just have imaging data, MRI data. We also have PET scan, different kind of imaging data. We also have a genetic information and also the CSF, which is biospecimen data, and also clinical data, right? And interestingly, okay, this is another slide. Not every subject have all the measurements. This is just exactly what Martin said, right? And what we see, this is not very typical missing data, what I call the block missing data. That some subjects could have entire columns of data missing. So it's very different from typical missing data we talk about as statistician, intermittent missing, or dropout study. And here's like, for some subjects, they have no CSF. For some subjects, they have no genetic information. We have this. How can we do data integration? Now, there are many reasons why we have this kind of data, because you have a high cost to measure. And a lot of times, there's just no need to have this kind of measurements. If you know someone has very severe progression, certain information, it's like obvious. You don't need to do all this kind of tests, okay? So how can we do good data integration for this kind of missing data? Now, actually, someone also mentioned about statistician and engineering, CS. We think this kind of problem very quite differently. As a statistician, we have an advantage because when we deal with missing data, we not just think about the missing complete at random. But when I work on some other paper, when I also studied the simulated data based on CS people, I was surprisingly seeing that most of the data, they think missing data is missing complete at random. Now for us, it's impossible. Why? And for this situation, it's actually informative missing, okay? So this is something we can think about our strengths and advantages as a statistician compared to CS or engineering people. But actually, we shouldn't limit ourselves just for medical imaging data. Okay, this is the kind of most well-used data in AI or deep learning called MNIST data, right? How many of you, your students, work on this data? I was going to talk about the deep learning. Someone mentioned, right? These are handwritten numbers. Actually, deep learning is doing very, very successfully. I will show later, I will tell you why. You're doing this kind of training accuracy is 99%. Even testing, using testing data, it's also close to 99%, right? You're doing all this CNN. But let's say I'm doing some other, in what situation? Some actually want, the Muhammad actually asked this question. In what situation CNN could perform really, really badly? This is a very simple example. You generate this data. What does data look like, okay? Now, you might think, because this is something another, why doing this kind of simulated data? Because a lot of you doing the tumor cancer, the tumor is already formulated, right? I think I always ask myself, if a tumor is already formulated, pretty much every imaging analysis could identify, right? It's no big deal, the tumor is here. But this is something related we call a tumor-associated microvesicles. That tiny, tiny microvesicles. Every normal person, we have a lot of microvesicles all over the body. The scale of the microvesicle is very, very small. It's only about 100 nanometers. So small that the microvesicle can go through your blood vessels in and out, okay? So this is the difference between the potentially cancer patient and the normal one. So if someone will eventually develop invasive cancer, they have very high concentration of a tumor-associated microvesicles. It's kind of cancer, the shape, okay? So this is the synthetic data we generate. And it's not working now. So I'm just doing even a weak signal. You can use a pulse sound processor to generate this data. Using the CNN, you clearly see that even you have a weak signal or strong signal, your accuracy is not that high. Especially your sensitivity is very low. It's below 20% of sensitivity. Your specificity is high. The true negative is high, but true positive is very low. You ask why, okay? The reason because it's very difficult to do it because you have very noisy background and you have a high heterogeneity. That every different subjects, their signal patterns are different, okay? So this is a problem. Seems the click doesn't work. Now, this is the real data. I work on this called optical imaging. I think the optical imaging is the most cutting edge medical imaging compared to the ultrasound, compared to the fMRI. So all this with a 4 modality, they have very intrinsic molecular contrast. Okay, molecular contrast is that they can see different layer or level of a molecular contrast in your body. Some is more surface, smaller, some is deeper. The reason because this is much more high technology. Remember that light it's a much compared to the ultrasound, it can penetrate deeper because it's a longer wavelength, right? As the light is much shorter wavelength, it has a disadvantage because you cannot penetrate deeper. So if you want to do the medical imaging, you want to see something deep, doing this light imaging, optical imaging is very difficult. But this one, they're doing the multiphotons, they're able to penetrate much deeper, okay? And also it's label-free, you don't have a radiation, things like that. It's a non-invasive, real-time in vivo imaging. So this is the real data. You have a normal one, have a 4 modality, and the other one is a cancer one. You can see the overall, the background is really noisy, okay? See all the strong, this line, circle, doesn't matter. The circle usually related to the fat, your fatty cell in your body. And what you care about is a very weak signal background, which is all the dots, right? The concentration and the patterns. This is what we call tumor-associated microvesicles. So if we are able to identify this kind of highly concentrated tumor-associated microvesicle, we are able to eventually to tell that the person eventually will develop invasive cancer before the tumor is formulated, okay? So you can see for this one, what is CNN performance. Actually, we do all kinds of tuning, okay? Your accuracy is 85%, sensitivity is still 70%. Let's say compared to minister data, it's much lower, okay? Specificity, true negative, no big deal, because in cancer study, we really care about the true positive. Of course, we also care about true negative, but true positive is more relevant. You don't want to miss any serious patient. So this is something what, besides the interpretation when you're using deep learning CNN, is like when you're dealing with the small samples, when you have a high heterogeneous population, actually deep learning, this type of a tool doesn't do that well. Well, why? Because they don't have a large training samples. They don't have this kind of uniform signals, and therefore they cannot do a very good job. Okay, so this is something. And I'm also going to talk about generative deep learning. Now, when I give a short course about deep learning, this example is always the most kind of a successful story. Talk about how successful a deep learning using AlphaFold. Okay. Now, this is the red, the green and the blue. The green is experimental result, and the blue one is a computational. Using the AlphaFold can predict it pretty well. This actually is a predict the protein structure of a SARS-CoV, okay, the protein virus. If you look at the surface, you see they're doing really well, right? Especially with the fatty lines, you see they seem to cover very well. But if you look more carefully, there's something doesn't really, it's here, there, it's not really matched. Maybe you think it's no big deal. Now, this is what I want to say something, that the challenge part is a part of the image are important for disease diagnostic, yet they are poorly predicted due to the limited training samples. It's kind of like you have kind of like your outlier, right? Like you're doing extreme series, you're doing the risk prediction. It's a large population, you can do very good prediction, but they're really not that important. You really care about their small one. The small one is the one you care about, the like extreme outliers, okay? So in that sense, this also little tails, which doesn't match with the green one, actually this maybe tell us the disease, something different. We actually don't care about the one match pretty well, okay? This is something I think we should think carefully and also challenge ourselves that the fundamental reason that if the training data doesn't represent the testing data, we will get very biased and misleading conclusion, okay? So I think one of the very challenging issues is about integration of the data, integrate the data for the heterogeneity samples. If the samples are homogeneous related, integration is easy, right? That's what we call population model. But if it's a heterogeneous sample, you try to integrate the information, it's very, very challenging. Another thing I want to say about this training data is not representative for testing. You might have heard about that. If any senator of the US, if they're Latino, Hispanic, or African American, you take their mug shot and you put it in the computer, and you know what? They have a high chance they're identified, they're criminals, okay, compared to the Caucasian senator. This again tells you the trustworthiness of AI. Why? Because right? It's a racial bias, right? When your training sample, your most criminals is it's like a Hispanic, Latino, African American. Then even you put a senator their picture, even, of course they're not criminals, you will identify them as a criminals, okay? So also we know that in US, all the presidents are Caucasian male except Obama, right? So if you put Obama, if you try to generate Obama, he is not black, he's white, okay? So this is something that if we want to get a trusted AI, we really need to think very carefully, is our training data is really representative for our testing data, okay? Another thing I think it's very, very challenging about these days, I think about, because when I'm doing the differential privacy, especially for correlated data, I want to get the synthetic data with the same dependent structure. I run into this problem that how can I generate a density distribution accurately, Okay, this is the same question for image data. This is actually very difficult. In statistics, we always think very simple as, generate density function. But this is for like a low dimensional, you can generate. But for high dimensional data, especially you have a multi-source, 3D, 4D, 6D, this kind of imaging data, how can you generate this distribution function really accurately? Especially this distribution function can capture the dependency, okay, among the data. So this is what we try to develop as a fair and trustworthy related to in the imaging data. My last slide is a summary. It's a kind of general question. What can statisticians contribute for imaging analysis? I think Martin did a very good job, right? And I think I was inspired by Hauda's brief talk in Lisbon, that we need to ask ourselves, we need to find the most important problems to work with, right? And if we are not working on the most important problem, we need to also ask ourselves, what things prevent us to work on these important problems? Of course, all of you have a different thinking, what are the important problems? I think you definitely should not say, I work on the problems so I can get published, I can get published in top 4 journals, I can get promoted, I can get awards. I feel this is just very, very wrong thinking, right? This is actually during Lisbon workshop, someone mentioned, the COPS committee, someone mentioned, saying, if someone is always chasing the awards, this actually devalues the award itself, okay? So I was just thinking about really just for our field, we should say, what are the most important problems we should work on it? And why, if we know, what things prevent us to work on these problems, right? And we need to think more creatively, and we try to solve some real problems. And really, I think innovation is very important, okay? Especially like innovative method and algorithm. And in the meantime, we should worry less about developing theory for the purpose of developing theory. Actually, I want to say something. Good theory should play an impact role for the applications. If the theory is not really doing play the important role for the application purpose, I think we're wasting our time to develop this theory, not just pure theory, okay? So again, I want to, lastly, I want to emphasize, we need to utilize our strengths. We shouldn't see, like Muhammad mentioned, I feel dismal because the field of AI grows so fast, right? Especially like ChatGPT, AI things, and we always feel we're left behind. We are chasing something. But in the meanwhile, I'm doing a lot of machine learning problems like recommender system. I see our strengths, that we actually think are quite different from the engineering or CS people. The reason because, like for example, even just I mentioned about the missing data, like I was shocked seeing that all they're thinking about is missing complete at random. I mean, 80% of a statistician now will not think about missing data just for missing complete at random. We have other knowledge, especially, let's say, uncertainty, variation, variability, this kind of heterogeneity, right? This kind of problems. So interpretation, interpretability. So I think there are a lot of work we can develop and really strengthen our field, okay? So this is my end of talk. Thank you.
I think we can take one or two questions before we head into the break. Yeah, I have a so go ahead.
So Annie, you mentioned to pick important problem and that solve real problems. And earlier, Susan also mentioned the issue with that students. So how do you motivate your student? I really appreciate when you explain the examples. You sound like you know a lot about the disease itself, about the conditions. So how do you train your student to be more like you?
Very good question, right? Usually, I always tell my students, say, don't just sit inside your room, like Chinese say, 空中造车 means build a car in the air, okay? I said, I want to really see at least find some real data problem, right? So I would say a lot of us new statistical methodology we did in our lab, in our team, that really because real data motivate us to develop a new methodology. For example, the mobile health data, we saw the multi-resolutional data. And it's a very different data that typically we see. Like when I did a lot of longitudinal data, but when I do the mobile health data, I see that we have a multivariate time series data, and as the resolutions are different, cross subjects, they are different, right? And the missing patterns, they are different. So how can you address this type of problems? And I think for imaging, for this photonic data, the optical imaging data, I actually took the initiative, talked to the bioengineering faculty, and then he actually come to my office and say, look, it's my sabbatical leave. I really want to learn statistics as well. So he explained all this optical imaging data to me. So, and because we see this very unique, like a weak signal, but very strong noise background, I don't see this kind of problem in medical imaging like a brain imaging, because brain imaging is a very structured. I know where the hippocampal area is, but for this breast cancer imaging, like I don't even know what this microvesicle, where they're located. Everyone's different. So I really think about, so that's another, like none of my students really work on the same problem. Because once they come to work with me, I say, tell me what area you're really excited about. Some say, I'm excited about causal. I say, I don't do much causal, but it's fine, let's do causal, okay? So we do some causal inference paper. And another student said, I want to work on the network data. I said, I don't have any experience on network data, but it's fine. And then we published several papers on network data. So you will see that my publications like in every area. This is because my students have all different interests. I don't want to tell my students, say, this is my area. I'm comfortable. I really also want to push the students out of their comfort zone. Also, I usually ask them, don't work on the same problems, same type of project for all your thesis. You want to publish 3 papers, best way is to have 3 very different problems. Okay, 3 different, so they really learn. But they also get some at a disadvantage. And if you stick with one, you're already familiar, you do fast. But I really just feel I feel bored. For me, myself, if I work on always same thing all my life, I feel bored, okay? But maybe for other people, I think it's not the same case. So, yeah, so I think, again, the different students, it's a very unique individual. You need to address like a heterogeneity interest and work the best. Like some students, I say, look, some students just not very good at a theory, right? I said, don't worry about it. I said, if you have a strong methodology and innovative idea, we can still publish well. Don't worry about that because you couldn't have a theory, so you cannot publish in top 4 journals. But sadly, we have to say all the biometrical JSSB, JASA, TNM, and also what's the other one? Annals, right? They all require theory. If you don't have a theory, so that's I just think about that's a problem of a field, right? Even you have a great idea, you cannot publish top 4. I mean, except the JADA have a case application study, right? But that's wrong. I just feel that. Okay, yeah.
So I think, I know there's still a lot of thoughts, but fortunately we have an afternoon breakout session to explore further of the 1 through 6 and then how to train our students to be like Annie, Hongtu, Martin, we can all dream big. So let's take a quick break and come back maybe 11:40 that we can go into the next session. Thank you.
for two reasons. Number one, I want to give them more time. Number two, I don't want to embarrass myself because I'm very regarded professors, but I don't want to sort of shout, speak with those four speakers. And the first one is Professor Xifeng Lin. She's a professor and a former chair of biostatistics at Harvard University. And she also has a number of affiliations. Because of the time, I'm not going to go through. So her research is on developing statistical methods and machine learning methods for massive and larger data and complex data set, and particularly in genomic data. And she has been supported by NIH through Marriott Award and outstanding investigators. Like what Tianxi said, how do you train your student to be like Annie? I actually like to train myself to be like a Xifeng, and obviously I was not successful. So anyway, and she's members of National Academy of Science, National Academy of Medicine, all those awards. So I don't fully agree with Annie in the sense you have to do important things to get those awards. And I think Xifeng, I don't think Xifeng chased after work, but she did important work to get recognition that she deserves. I think that's a good thing. So I like to do the same thing too. Anyway, without further ado, I'd like to have Xifeng begin the first speaker.
Thank you, Heping. That's really, really generous introduction. And so this is something I admire Heping, like his work on reproductive health, women's reproductive health has been inspired me a lot through my career. And one thing I want to mention, and is like Heping mentioned, you do important work to get award. But I feel like we do important work in order to change the world. I think that probably will be more important to me to really help the world and to make an impact in science. And I think this is older one, Philip. It's a new one. Sorry about that. Oh, no, that's okay. I just use this one. Yeah. No. I mean the slides. This is old. Yeah, let me try this one. Oh, this one doesn't work. Oh, here we go. Oh, sorry. No, should I? Oh, this go backward, right? I think this is the older one.
Okay. Do you mind sharing it again?
No, I emailed him this morning. Yeah, that's okay. We'll start talking. And so I think, so I'll share with you the license I learned from analyzing the whole genome sequencing data. And I feel that I will make a few points, and I think a lot of them echo what has been said. And so how can we analyze this type of large data by integrating statistics, machine learning, and also AI, and in the important problems.
Just give me 2 minutes and we'll update.
Okay, great. Okay, sure. For 2 minutes. Yeah, so one thing I feel I really inspired by the previous discussion is that how we want to identify important problem and also how we want to train students. Another thing I did not get a chance to ask Annie is how can we change the curriculum? And we did not have a chance to talk about this. This is really important for us, I think for all of us. And so because we all want to change the students with the newer knowledge base, but when we want to add new courses, we have to subtract. So I have to, the paper probably this afternoon we can talk about it, right? How can we train our students? And so what we want to add to our curriculum and what we want to subtract in our curriculum to make the training more feasible. And it's difficult to train, we want the student to have this kind of T training, and so basically have both the breadth and depth, but it's impossible for the student to have this type of training and to know everything in 5 years. So therefore, we have to really figure out what type of breadth we want to have and what type of depth and we want to have. So hopefully in the afternoon when we talk about have a deeper discussions, and then we can talk about what kind of depths we want to have and what kind of breadth to have. So for example, like we talk about Hong Tu made a similar point, engineering. I'm going to talk about I'll make a similar point about computation engineering. Our students, we have now trained them to be the software engineers. How can we train the student? And the students generally don't have that background. It's difficult for the student to learn both software engineering. That means a real software engineering, not just start developing our package. A real software engineering, developing the database, and developing both the front end and the back end. So when one develops software, we'll have to think about both front end and back end. Back end basically is the database, and the front end is the query. And so we have now trained the student to do those type of things. And so do we really want the student to learn those type of things besides the methodology, statistical methodology, and also besides the domain science? Multiple people mentioned the domain science as well. You found it, Philip? Oh, okay, sorry about that. And so maybe while they are looking for this, we can start some discussion about this, right? Yeah, so for example, Susan, I would love to hear. So for the curriculum, what should we subtract? What should we add?
But I was wondering, I don't know if this is a good idea, this idea I'm gonna suggest, but I know in some other departments, like in CS, they just have to take 10 classes. A certain number have to be in CS. You know, at most 2 can be outside of CS. And usually the advisor determines, like each person associates themselves with an advisor, and the advisor suggests to the person what particular CS courses, like it could be totally theoretical, all probability type courses, or it could be something totally different. And I don't know if maybe a solution in stat and biostat, a potential way forward in stat and biostat is to have more freedom to the student, but the advisor, of course, would provide advice, right?
So one example in the Department of Biostatistics, University of Michigan, I think it maybe is a model that we can follow. It's about this computing course. We have 3 modules like C++, R, and Python. So whoever does not have the knowledge or experience of R, they can go to take R. Then if someone has interest of taking Python, they can go to take Python, right? So I don't know if we need really the whole semester for linear regression model, or should we have modular linear regression, generalized linear regression, or Cox regression as modular, and just to have a little bit faster training. I'm just thinking that have a little bit more flexibility for people to gain more data science sort of the training from statistics perspective.
I know your slides are up, but I just want to add that I also want to come back to the training students thing. I think I don't think there's anything majorly wrong about our curriculum. I think it's about we don't throw our students into the jungle enough. We don't expose them to real. We're too protective. Like all our courses gave them textbook problems. We never give them problem that is realistic, so they become fearful of the real thing. So sometimes I just think that we don't need to add much. We need to add 1 or 2 courses where they're learning the jungle skills, then they learn how to learn on the job, then they jump into research, then they can continue to learn on the job. Those
Those are all great points, so we can continue those discussions in the afternoon. Okay, that doesn't count my time, right? Okay, so basically I want to tell you, basically this is more like a storytelling and what I have learned by analyzing the whole genome sequencing data, building the infrastructure, and also help the science, and using both statistics, machine learning, and AI. So maybe I give a quick overview of the timeline of the whole genome sequencing effort. And so about 20 years ago, that was the completion of the whole genome and sequencing that basically sequenced one person, very, very expensive. And then about 15 years ago, that was a completion of the 1,000 genome program, a sequence about a couple thousand people. It's still very expensive, only the depth is pretty low. In the last couple years, several large whole genome sequencing programs have been launched, both in the US and also in the world. And the most well-known one is called the Transomic Precision Medicine Program, called the TopMed. We have sequenced about 190,000 people. And the other is the genome sequencing program by NIGRI. We have sequenced about 350,000 people. And both those data are available and, in the cloud. And the TopMed are available in NHLBI Biodata Catalyst. This is NHLBI ecosystem. And the genome sequencing program is available in Anvil. So that is the NHGRI ecosystem. And also multiple biobank has been launched, including the most well-known one, UK Biobank, and just a couple weeks ago, and the UK Biobank has announced the 500,000 people whole genome sequencing data are available in the cloud. That is the RAP. And also, Million Veteran Program plan to sequence 1 million people. ALPHAS used to be called the Precision Medicine Program by Obama administration, and later on it changed called ALPHAS. And so the plan to enroll 1 million people, and also sequence them, integrate the genomic data, epidemiological data, and the electronic medical record. And so this is the current status of ALPHAS. And so the plan is to enroll 1 million people across the US. And so far has enrolled about 700,000 people, you can see across many different states. And so with electronic medical record and also biosamples. And so far have sequenced about 250,000 whole genome, and the data are on Anvil. And so the data all cannot be downloaded, all in the cloud. So give you a sense how big the data are. So this is the TopMed, a freeze 10, about 190,000 sample. Before the QC, there are about 1 billion variants. And so after the QC, there are about 855 million variants. So the data we deal with are very, very large. So the scalability is critically important. And as you look at the data, and so majority of the data are the rare variants. For example, 45% of the variants are singleton. That means among those 200,000 people, only one person has it. And 15% are doubletons, and then only less than 1% are common variants covered by the GWAS chip. And so what is the goal? The scientific goal is we want to scan the whole genome to identify the genetic variant set or the mass associated with the human diseases. We don't care whether the whole genome is associated with the diseases. That's not useful for drug discovery. And so we want to see a particular gene or particular mask and of the gene associated with the human diseases, and this can help with the drug discovery. So then the question is, how can we do that? So what are the challenges? First, how can we define the variant set? And so use this example. Suppose the outcomes, the station called outcome, and in genetics called phenotype, is LDL, this is bad cholesterol, low is bad, high is low is good, high is bad. And then we want to see how the variants, for example, in the ApoE enhancer, suppose there are 100 variants associated with LDL. We control for the covariates and X and X, and then here, because if you want to do 100-degree freedom test, so basically there's very little power. But if I know there are only 4 signals, so really the causal variance, and with beta not equal to 0, we want to do 4-degree freedom test. But this is impossible in practice, and this is completely oracle. And also the SNP are correlated. So the question is, how can you empower real-variance association test without doing this 100-degree freedom test? And so basically the main idea is, suppose you calculate the marginal association statistics of each SNP and the phenotype, we want to aggregate them across those 100 variants in the ApoE enhancer. But how can we aggregate them? So in order to do that, we have to build, first we need to build the infrastructure. And so the first, we need to build a whole genome sequencing integrated analytic ecosystem. And so the most statistician, we are not trained as a software engineer. But I want to make the point, it's worthwhile for statistician invest ourselves to build data and analytic infrastructure and also computer engineering. If we wait for others to develop those things for us, it's too late. And we are likely to make an impact. Okay. So to show you, so in order to do this analysis, we have a genetic variance and also the biological function of the variance and the phenotype statistician called outcome, like LDL. And first of all, we want to integrate the functions and in the genetic analysis, and basically if the variants had more biological function, we want to give them more weight. This will help with the discovery. And so the next part is we want to understand the causal pathway. And so basically this is where the causal inference come in by integrating the whole genome sequencing data with other type of functional data like multi-omic data. And then the endpoint is the action. So that includes the prevention intervention strategy and treatment target and the new drug discovery. And so this is optimal. So in order to do that and to do this whole pipeline, we need to do some homework in the infrastructure building. And so the first infrastructure building, I'm going to focus on it to do the top. I'm not going to talk about the bottom. And so how can we do the functional annotation? And to this end, it's important for statisticians to get involved in a large consortia. And so for the whole genome sequencing, for the genome sequencing program by NIGI, and we have this genome sequencing program annotation working group I chaired. And so the idea is to integrate multiple functional data from many different sources, and such as the ENCODE, roadmap, and so on, into this large database and GTAC. And so we include over 300 annotation, 80% are built on 38. This include allele frequency, conservation score, protein functions, epigenetic score, and many others. And so if one think about the whole genome, totally there are 3 billion positions. And each position, there are 3 alternate variants. So totally, this database has 9 billion variants. And so this is a huge, huge, huge database. And so basically, I don't know, I was never trained to be a software engineer. I never trained to do the database. So, but in order to do this, we have to build a relational database. And so this is the PostgreSQL. So I hired a computational biologist. I hired a software engineer. I know what I need, but I don't know the technical detail. I don't need to know the technical detail. They are much better than me. And build this whole relational database, and also with very efficient indexing, and can query it and to find a particular variance in less than 1 second. And also, so for this is publicly available, and one can do the query for a single variance, or variance in a gene, variance in a region, or you can do batch annotation. And because if you look at the TopMed data has about 1 billion variants, so I need to pick from this 9 billion variants database, pick up this 1 billion variants. But in UK Biobank, and they have 1 billion variants as well. But UK Biobank, this 1 billion variants are different from the TopMed 1 billion variants. So basically, you have to do this type of annotation very, very quickly. And also, in order to understand this, and because many of the users, they don't have computational biology background, they don't have the really genetics background, so we have to make it useful and for the users. So what we did was we built this Favor GPT. And so basically, try to help the users and to harvest the power of a large language model to improve the user experience using the Favor, this 9 billion variance database. So this, you can see the software engineering generally involve backend and also front end. Backend is a database, and so what we have the PostgreSQL. Front end is basically how can you do the query. And so basically, we built the Favor GPT and using the Favor API, and which include the ChatGPT-4 API and also Llama 2 API. So basically, we integrate this 9 billion Favor variance database and the documentation with the large language model API, which include the ChatGPT-4 API and also Llama 2. Llama 2 is by Meta, and Llama 2 is open source and compared to ChatGPT-4. So that is easier when we build the APIs. And so basically, those are the first person, Tom Lee, is a high school student. And so it's really, those high school students are brilliant. And so we have new software engineer and computational biologists. And so we basically have built this Favor GPT by integrating this 9 billion variance functional annotation database and also with this front-end interface. And so using the large language model GPI, this can do very, very user-friendly query and also easier for people to understand. So for example, this is the front page of the Favor website. So basically you type in your query, and so just say, even somebody knows nothing about genetics, you can say, provide the functional information of BRCA1, or provide functional information of particular variants, or ask how many pathogenic variants does BRCA1 have, and then that will calculate, BRCA1 has 15 pathogenic variants, just looking at that database. So this is really easy for people to use. You don't need to do any programming, and so this is really convenient. Okay, now we have everything those built up. And so the next thing is how can we borrow this infrastructure into the analysis? And so what we do is, like, suppose you have the data from the TopMed data or UK Biobank data. And and also we have this backend database, functional annotation database with 9 billion variants. And we make that available in all those cloud ecosystem, like NHGRI is Anvil, and NHLBI about Data Catalyst, and also the UKB is RAP. So we'll work with all of them closely, because that is what you have to be in the club. You need to build a relationship. They build this kind of a trust. People trust you, then you can work with them. So for example, for the TopMed data, we have this annotated data in Data Catalyst offered to all TopMed investigators, and they use it. And that makes things much easier. So you have built this type of reputation. And now, for the whole genome sequencing data, the data generally are stored in VCF format. And so basically, first thing you need to do is to QC the data. And so my colleague at Broad Institute, Ben Neal's group, developed the Hill, and that can be used to QC the data. So Ben's group and I, we work closely together. And then the next step is, suppose in TopMed data is there 1 billion variants, and then we need to use this backend database to annotate this 1 billion variants. So basically, we build this Favor annotator, and that basically is a script that can be used to annotate this 1 billion variants in TopMed or in the UK Biobank. And also, VCF files are too big. These are not used for large biobank size whole genome sequencing data. So basically, we use the GDS format, and including the annotation, and the compression rate is over 1,000 times. So cloud are beautiful, but cloud is expensive. So the data storage is expensive. So if one reduce from couple hundred terabytes data to 100 gigabytes data, that costs you nothing. Okay, and so one of my colleagues at Stanford and his lab members tried to use the cloud, Google Cloud, and they now realize it's so expensive. And then by the end, he couldn't have enough funding from the grant to pay the cloud cost. He had to use his discretionary fund and to make up the cloud cost. So therefore, scalability and cost efficiency is critically important to us, and to make the method used. Now we have all those infrastructure built, and then the analysis pipeline we call the STAR pipeline that can be used for whole genome sequencing analysis. And one might wonder how much it costs to annotate the genome with a billion variants. It turns out we can make it cost only $24 in 3 hours. So that costs nothing. So that is very important. Whatever we want people to use, it has to be scalable, it has to be computationally efficient and cost efficient as well. Now we are ready. And so basically what we have been doing is to work with multiple NIH ecosystem and also the UK Biobank ecosystem. And so basically do a different way to do the data sharing. The old way to do data sharing is basically cluster model. So basically you copy the UK Biobank data, Kenzie make a copy, I make a copy, and both of us have 2 different copies, the same data, and that's really not cost efficient. If 100 people in the room, we make 100 copies to our own computational cluster. So basically that is data sharing is the same as data copies. That is not efficient way to sharing the data. And because whole genome sequencing data too expensive and too big. And so right now the change to the model is bring the researcher to the shared data through the cloud, also only 1 copy. For example, like UK Biobank whole genome sequencing data is in wrap by DNA nucleus, everybody access the same data. And in order to do that, one need to get familiar with workflow description language like WDL, and also need to be familiar with the workspace and the AppleEd. And also Anvil, the genome sequencing data are in Anvil. So GRAD and also AlphaS data are in Anvil as well. And so basically one need to get familiar with those kind of cloud ecosystem. And the top-my data are in Biodata Catalyst. Gradually, the DB gap will disappear. And so this will be replaced by those NIH ecosystem. Okay, so the next point I want to make is empower real-variance association test by incorporating functional annotation. So basically the key point is to integrate the domain knowledge and in statistical inference. This will help increase the impact of statistics in science. So that basically means we need to learn, like in my field, we need to learn genetics. We need to have my student postdoc learn genetics in order to make the method really useful and make an impact. Okay, so how can we do that? And so this work was co-led by my former students. And also, the other thing is we need to publish in non-statistical journals. And so like the first paper was published in Nature Genetics. And the second paper, we want to make everything automated. And so we create a whole pipeline. And that was published in Nature Method last year. So the idea is to empower real-variance association test by dynamically upweighting the functional variance using multidimensional annotation score. So here is the pipeline. So basically we use so first we create the phenotype and a covariates and also sparse GRM matrix, and also we annotate the data. And so as I mentioned, BCFL is not scalable for large-scale whole genome sequencing study, so basically we use the GDS format. That compression rate is over 1,000 times. It's much, much cost-effective for dealing with the large data. For common variants, we can do the single SNP analysis. For rare variants, we can do either the gene-centric analysis or genetic region analysis using the coding mask or non-coding mask. And for the coding mask, one can group the variants. Basically, they all analysis, you have to know the biology. And so including for the coding mask, we group the variants into loss functional variants, or the missense variants, or synonymous variants. And for the non-coding variants, we group them into enhancer and promoters. And also one can do the sliding window approach. One challenge is when one analyzes non-coding variants, it generates functionality are tissue and cell specific. So the non-coding variants analysis is more challenging. And so to annotate the data, so basically because there are many, many different annotations. For example, if one look at the protein function, there are over 10 protein functional score. And also for epigenetics from the ENCODE, there are over 30 epigenetic scores. So first, we need to do some dimension reduction. So what we do is we use a principal component. This we call the annotation PC. And for example, for the 30 epigenetic score, we calculate the first principal component. For the 10 conservation score, we calculate the first principal component, and so on. And then basically, when we talk about functionality, the variance functionality cannot be captured in a single dimension. So if you look at the heat map, the correlation about epigenetic function and also conservation score has very little correlation. So that's why we need to use multidimensional annotation. And so here is the analysis workflow. So we had input the data, and then we run the favorite annotator to annotate the top metadata. So create annotation score for each of the variants, use multi-dimension. There is a black screen. Is something broken? Oh, really? Okay. Yeah, that's right. This basically is the dimension reduction or embedding. You can think about the embedding is a fancy way of saying dimension reduction, basically. Yeah. So then we create those kind of annotation. Now we can do group the variants into different masks. And so for each gene, we group the variants into loss functional variants, or the missense variants, or synonymous variants, or promoter and enhancer. And then we can run analysis and using a different weight function. And then we aggregate those weight functions, aggregate those different tests. And I'll explain what those different tests are. And so we call this star method. Then by the end, we create for each mask, we have association, like the ApoE enhancer and the LDL association, or ApoE promoter and LDL association. And so, but the question is, with many different functional weight, how can one combine the test with a different weight? So that's basically where the art is. So the traditional way, when we did this 10 years ago, and so basically one can develop this kind of burden test was that test. So for the burden test, so basically you got this kind of individual association statistic. Basically you can think about the G transpose Y. And then this is your, for ApoE enhancer, you have 100 association statistics. You aggregate them, either using the linear combination or quadratic combination. And for the linear combination, so it is powerful when the effects are all in the same direction, because if the beta are all in the same direction, the linear combination will work out well. But when the effects are in different directions, and then the burden test will be a lousy choice, and then you want to do the quadratic test. And in that situation, basically this derived from the kernel machine framework, but turns out it has a very simple expression. And so this SCAD paper has been widely used in analyzing the whole genome sequencing data. And now, so this can be particularly useful, and when the variants are in different directions, especially in the non-coding regions, the enhancer and the promoter. Then the question is, ideally what we want is for that weight function, if among the 100 variants, I know there are only 4 of them, beta not equal to 0, I want to give the weight 1 to those 4 variants and weight 0 for the other But in reality, we don't know they are 4, and we don't know what they are. So therefore, what we do is we use this kind of Cauchy combination method and to combine correlated p-values. And so this is really a beautiful method when you deal with the test. We don't know there's a uniformly most powerful test, and you can try different tests to see which one give you the smallest p-value. If you use that, the smallest p-value to report as your final test, you're cheating because you look at the data multiple times. But the Cauchy combination test basically create a beautiful way to combine different correlated tests. And so basically it can be used to combine the SNP level p-value test, or it combines the p-values with, oh, this is even worse. Yay! Yay, thank you. Oh, so still one more. Oh, here we go. It works, thank you. Okay, and use the different weight. So let me show you how that Cauchy combination test works. So when you have a correlated test, and so traditional way to combine the correlated test is the Fisher combination test. And but this has a problem. And because when the tests are independent, and the Fisher combination test has basically 2B degree freedom test. But when the p-value are correlated, and this is not a chi-square test anymore. And so how can we account for that? So basically this Cauchy combination method create a beautiful way to combine the correlated p-value. So we don't like Cauchy. Generally, Cauchy doesn't have the mean. Cauchy doesn't have the variance. But it's really this kind of heavy tail distribution is really beautiful way to combine correlated p-values. And so the reason is, and no matter what is a p-value distribution look like, and the joint distribution look like, and the sum of Cauchy and still Cauchy in the tail, no matter what correlation you have. And so therefore, if you can see if we apply different tests to the same data set, all the p-value are correlated. But when we use a Cauchy to combine those p-values, still Cauchy, and the computation is super, super quick. So that makes things much, much easier to work with. And so this paper was first published in American Journal of Human Genetics and later in JASA. So that's basically how that works. So for example, if I want to test the ApoE enhancer, how it's associated with LDL, there are 100 variants, we can use Mendeleev frequency as a weight, run the scatter p-value, and then we do a Cauchy transformation, or you use the epigenetics APC as a weight, calculate the scatter p-value, do a Cauchy combination, or APC conservation as a weight, calculate the scatter p-value, do a Cauchy combination. We combine them using this Cauchy ACAT method, and computationally super, super fast is less than 1 second. And so we don't need to worry about the correlation at all. So that is very nice, and the accuracy is very good. And so for us, scalability is quickly important. So you can see for analyze the 500,000 people whole genome in UKB, and so for gene-centric analysis only take 1 hour. So that is very good. So here are the results for the top 30,000 people. You can see that for analyzing the different mask and LDL, the loss functional variance of PCSK9 is associated with LDL, and that's already a drug targeted, approved by FDA for PCSK9, and also NPC1L1 of missense variants is also associated with LDL, already a drug approved for that by FDA as well. So that's all encouraging. And the one thing is one can see that for the promoter and the enhancers, those are non-coding variants, the signals are weaker. So the one question is how can we improve the power of detecting enhancer and promoter region? And the answer is we have a postdoc of mine developed this cell star, and the idea is to integrate cell-specific functional annotation and using the single-cell data and the CRISPR and the perturbation data, and from the catalyst and or from the human cell atlas and or from the NIGR IGVF. So basically, you do the functional right, and then that will for the non-coding variants, that will provide a better discovery for the whole genome sequencing analysis. So this really creates a beautiful context for integrating different type of data. But when we do the data integration, we need to have a scientific problem in mind. So because you can have many different ways to do data integration, but how to integrate the data need to be driven by the scientific problem. Okay, so this is the last part of the talk. And so we did this work, and 10 years ago and also a couple years ago developed the STAR method. But we asked ourselves that 10 years later, is this the best we can do? And so here is that we are going to talk about how we can do the reverse association test using ensemble testing. So ensemble method has been widely used for prediction purpose, but our goal is not for prediction. Our goal is inference. And so we want to see how can we do ensemble inference. And so this paper was published, it will appear in GSSB, and led by my postdoc, former postdoc Yao Liu. So here, I will present a simple context to understand the idea. So if you think about very simple regression, y equal to x beta. And I want to say, suppose the beta are all in the same direction, all positive. So the SNP in the loss functional variance, generally they are all productive or harmful for disease. I want to test the beta equal to 0. And so in order to do this test, so the traditional burden test is you assume all the beta, you aggregate totally the total dose level, and then take the beta out. So that basically you assume beta is the same. And then to do this test, it's become 1 degree freedom test instead of 100 degree freedom test. And so basically the burden test, basically you aggregate the score statistic. A natural question is this the best we can do? So how can we develop scalable and powerful tests for testing beta equal to 0, this 100-dimensional beta? And so the challenge is the beta is multidimensional. The UMP test does not exist. And so for testing this multiple varied alternative tests, any test likelihood ratio test is not UMP test. It can lose power. So any test can perform poorly in a wide range of alternatives based on the Lehman lemma. So can we improve the power of this type of test? So the first question we ask ourselves, is this burden test the best one we can do if we know the signs are all in the same direction? The answer is no, because the burden test assumes all the beta to be the same, and but in reality, the beta can be in different directions, and even it can be in have different values. Some betas are big, some beta are small, and so the question is, how can we do better and to do this kind of a testing problem when we know that the likelihood ratio test is difficult to do in this kind of constrained problem, and it's not UMP test. And now let's think about for the prediction. And so for the prediction to do the learning, and so you can either find the best learner, and generally it is difficult and computational expensive. The other way to do is ensemble. That is very effective in practice. And for our problem, we are not interested in prediction. We are interested in inference. And so to identify a single best test generally is mathematically and computationally challenging. So that motivates us to ensemble and to do the ensemble inference. So how can we do the ensemble inference? Let's start from ensemble prediction, ensemble learning. So ensemble learning is a classical machine learning method for prediction purpose. So the idea is to combine many weak base learners and to obtain a final strong learner. And so you have a bunch of weak learners, and then, so basically each weak learner is weak, but the final learner is strong. So basically this is similar to the Chinese idiom saying, the wisdom of the masses exceed the wisest individual. 三个臭皮匠顶个诸葛亮 for those who know Chinese. Okay, so now this is for prediction purpose. Okay, so a classical way and to do the ensemble learning is random forest. So basically in this situation, the base learners are trees, and those trees are all weak learners. And so in order to build a strong learner, so you randomly select m variables. Generally, if you have 100 variables, you select 10. Take a square root of them. You want to make a tree independent. And then after you build you do that 1,000 times, and then you average those 1,000 trees. So basically this ensemble strategy is average, and base learner here is a tree. And so bagging it basically use all the variables, so that make all the tree correlated. The variance is too big, so bagging generally doesn't work as well as the random forest. But this is for prediction purpose. I don't care about the prediction, I care about the inference. So now let's think about the burden test. Suppose I know the true signal direction, and those are the right lines. And so I want to ask myself, if I project the score statistic to some kind of random direction, which direction is likely to give me the best power? The answer is the true signal direction. So the burden test, but if you think about the burden test basically is the sum of all the individual score statistics. So basically you project your score statistic to this 45-degree line. And even though I know the beta are positive, but I project to this 45-degree line. And so you can see if the true direction is not this 45-degree line, and then the burden direction will be a wrong direction, and those right direction, burden test will lose power, right? And so now, how can we find the better test than the burden test, given we don't know the true signal direction? So that is where this ensemble idea comes in. So basically, first you build a weak-based test. So how to build a weak-based test? We basically do the random projection and project the score statistic to the random direction. Suppose all the betas are positive, and then I simulate 1,000 random direction in the first quadrant. How can I simulate random direction in the first quadrant? So basically you simulate normal 0, 1, and you normalize it. That basically gives you the circle direction, the random direction. Now you project your score statistic to those 1,000 random direction. Many of those random directions are likely to be lousy direction. I don't care. As long as I have 1 or 2 directions which are closer to the true signal direction, I will be good, okay? But this also means that suppose you do this random projection of the score statistic 1,000 times, then you have 1,000 p-value. All those p-values are correlated. Many of those p-values are large because the directions are wrong, right? So averaging using the random forest strategy to do ensemble is a lousy idea, right? Because many of those directions are wrong, you're going to have a small number of directions to be right. So when we do ensemble, we are going to ensemble using ACAT. Use the Cauchy combination method, because this Cauchy combination method is very similar to the minimum p-value test. As long as 1 or 2 directions are right, that's going to give me that direction, and that gives me the best p-values. But it's better than the minimum p-test because I don't need to worry about the correlation. So that is really convenient. And we analyze the data using this ARIC whole genome sequencing data. So if we just look at the column on the right, and so we analyze lipid protein and neutroprophin. And so because we need to do this for a large number of time across the genome, so here we use allele frequency as a weight. So you can see if we don't ensemble, there are 6 discoveries for lipoprotein. But when we ensemble, we have 54, increase the discovery by 10 times. I did not have time to talk about ensemble scat, and one can also do that for ensemble scat. Then you can see when we ensemble it, and then increase the discovery by over 50%. So that is encouraging. To wrap up, and so this is the beautiful avocado, and so the beautiful Abu Dhabi. So first is it's important for the statistician to invest the time to do computer engineering and infrastructure building, and to build this kind of analytic ecosystem. And also it's important to make an impact in science. It's important to integrate domain knowledge in statistical inference. And also it's useful for us, because statistician, we care about the inference. It's useful to think about from ensemble prediction or ensemble learning to ensemble inference. So if this is ensemble inference, it's a good thing. And finally, scalability is important, and especially when we deal with the cloud nowadays. Thank you.
It's very unfortunate that we had some technical difficulties, and I was just informed that the food is being prepared, but the restaurant is ready, so we have to move into the lunch so that we can enjoy the food at its prime. So we will resume the session that didn't end. We will resume, starting with Q&A with Xihong after lunch. And thank you.